survey based on classification upon nature of field is R dash. So nature of field मतलब क्या है? Land, air and water. I hope you remember, right? And land based surveys were land survey, city survey, and topographic survey. So is number one counting? Yes. This is land or cadastral survey, hydrographic survey on water, astronomical survey on space, geological survey is not coming there. So these three are the options. So A, B, and C. These are the options. So this is a multiple select question. You should select A, B, and C. Then only full marks will come. If you only select A and B, 0 mark. Only select B and C, 0 mark. Only select A and C, 0 mark. If you select D also, you'll get 0 mark. There is no negative marking. Okay. The answers are A, B, and C. Yes. That's it. That is our entire discussion regarding our first chapter here. That is basic concepts. Okay. So that is the end of the first chapter now. So now we can move on to our next chapter here. So who is the next chapter? It is nothing but our, chain survey. So let us move on to our next chapter here. That is nothing but the chain survey. Okay. We'll just finish the introduction of this particular chapter, and the major discussion we can start tomorrow. Okay. We only have little time left here, but I think by this time we can finish the introduction towards this particular chapter. Okay. Yes. So we have successfully completed our first chapter. Okay. So we'll start with our second chapter here. That is linear measurements and the chain survey. So please remember, right? What is the first basic measurement that we have? The first basic measurement in surveying is what we call it as horizontal distance. Yes or no? Horizontal distance is measured by which instrument? Horizontal distance is measured by an instrument known as chain, and the survey is known as chain survey. Before we can start our discussion on chain surveying, we need to know what are the different methods of linear measurements. We need to know what are the different methods of linear measurements. What are the different ways in which a linear measurement can be taken. So in this, the first one is what we call it as direct distance measurement. So what happens in direct distance measurement? Please understand. Here, whatever measurements that we want to take, those particular measurements are measured directly in the field. For example, you imagine, I am asking you to measure the dimensions of your room. I am asking you to measure the dimensions of the room. You need to report the dimensions to me directly in the room itself. If you want to do that, what is the type of instrument you will use? Please tell me. If you want to measure and report the dimensions of your room, tell me what is the instrument, what is the basic instrument you can use for that? Please tell me. Any idea? Right, very good. You can use a tape or you can use a chain. That's it. Okay. You can either use a chain or a tape. You put the 0 meter end of your tape at one point, you extend the chain to the other point, you can measure the other dimension. That's it. Okay. Right. So here for direct distance measurements, you can use instruments like tape, chain, etc. You can use instruments like chain, tape, etc. This is direct distance measurement. I like it as DD. Right. The next measurement is what we call it as optical distance measurement or OD. So here what happens is we are not going to get the distances directly, but in fact we are going to use some optical measurements. We'll find some values, use formulas to calculate distances. Right. The best example of this method of measurement is tachymetry. That's what we can call it as tachymetry. So in tachymetry, right, we have an optical instrument that is nothing but a tachymeter. So tachymeter consists of a telescope that is nothing but an optical instrument. Using this telescope, I can take a staff reading S. I'll take staff reading S. Now I'll come back to my lab and I'll recalculate my distance using this formula K into S plus. In the field, I'll be measuring S1, S2, S3, S4. That's it. I'll come back to the lab and use these values to find D1, D2, D3, etc. So it's not direct, it's slightly indirect, and I'm using optical instruments for my machine. Right. The best example is TACM. Now, the third type of measurement is what we call it as electronic distance measurement. In short, we can call it as EDM. So, what is meant by EDM? Electronic distance measurement. ODM is optical distance, DDM is direct distance measurement. We are going to talk about electronic distance measurement. Why do we call it as electronic distance measurement? Because here we are going to use electromagnetic radiations to calculate distances. Let us try and bring out the idea here. So, you imagine that you are having a ground like this, and you need to measure the distance between, say, point A and say point B. These 2 point distance you want to measure. So you will keep your EDMI at this particular point A, it's an electronic instrument, and at the point B, you are supposed to keep a prism pole like this. Now, what you do is you sight your prism pole by the instrument, right, and you press measure button. Electromagnetic radiations will come like this. So these are electromagnetic radiations generated by the instrument. After hitting the prism pole, they will get reflected back like this. They'll get reflected back like this directly to our instrument. So what is that? That is a reflected radiation. Initially, what we thought is if we can measure or if you know the velocity of the radiation, and if you know the time taken for the radiations to go and come back, we can calculate the distance. It will be velocity into time by 2. Velocity into time will give me distance, but this time is for the radiations to go and come back. So we need to write velocity into time by 2. Yes. But the problem is the velocity of these radiations are very high. All electromagnetic radiations travel with the speed of light, that is 3 into 10 power 8 meter per second. That is how much? 3 into 10 power 8 meter per second is so long. Yes. So all electromagnetic radiations travel with the speed of light, right? And due to that, like measurement of time becomes very, very costly. Nowadays, we don't measure this transit time, absolutely not. We don't measure the transit time, but we measure something known as phase difference. We measure something known as phase difference between the emitted and the reflected radiation. Okay, so the emitted radiation will be having a equation of sine omega t. The reflected radiation will be having sine omega t plus pi by 2. What is this pi by 2? The pi by 2 is what we call it as the phase difference. That is the phase, PHAC, phase difference. Right, so now with electronics, advancement in electronics, I can measure this phase difference. Now, this is used to calculate distances. So if anybody asks you, how does an EDMI measure the distance? Your answer should be, it is measuring distances by measuring phase difference. Okay. So you see, so here, electromagnetic radiations are used. Your answer should be right. Now, what do you do? The phase difference between the emitted and the reflected radiations are used to calculate distances. Now, there are different varieties of EDMI. Please understand, there are different varieties of EDMI, and the classifications of EDMI are mostly based on what kind of radiations are you using. There are different types of electromagnetic radiations. For example, we have microwave, we have visible light, we have infrared, we have UV light. We have so many different types of electromagnetic radiation. Now, depending upon what type of EM radiation we are using, we have different types of EDMI. So this is the different types of EDMI that we have. Okay. So yeah, this is the different types of EDMI that I have. I have now just kept that particular notes as it is. I don't want to waste time writing about them. That is why I just keep that measurements like this. Okay. So the first set of instruments are electro-optic instruments. They use modulated lights. Examples are geodemeter, vicometer, arrangement. Okay. The next type of instruments uses microwave radiation. They are electrotape, distameter, Deccan navigator, microchain, and the last one is telluride. Third one is what we call it as the infrared emitting instrument. The examples are Distromat, which is made by a company known as Leica. They make very good total stations and all. It's a Switzerland-based company. Right. So these are the different types of EDMI based on the radiation study. For gate point of view, absolutely forget about this. Don't study. Gate point of view, not important. But for other theory-based examinations, yes, they can ask you. In Andhra Pradesh PSC in 2017, if I'm not wrong, they asked one question like this: which among the following instruments uses microwave? Option A, geodimeter. Option B, megometer. Option C, rangemeter. Option D, tellurometer. What is the correct answer? The correct answer is microwave emitting instrument is tellurometer. So like this, questions have been framed. Okay, in PSC level exams. Gate point of view, ignore. Gate point of view, you simply ignore. Right, that's it. Now, our methods of linear measurements will not be complete. It will be incomplete if we don't talk about the approximate methods. Even before having this EDMI and everything, we used to have approximate ways of distance measurement. In that, the first commonly used method is pacing. So what do you mean by pacing? Pacing is the process of measuring the distance between 2 points by counting the number of steps we have taken. Like I'm not dancing there, I'm walking, okay? I'm not dancing, we are walking. So this step that you take is what we call it as a pace. So if we are walking between 2 points and counting the number of steps, right? That way of measurement is what we call it as pace. One problem with this pacing is that the pace value need not be the same. The pace value need not be the same. Right? For a person who is having my height, he will have one value of pace. Right? For a person who is having, my height will have the same value of pace as me. A person shorter than me will have a lesser pace. A person taller than me will have a larger pace. So the pace value generally ranges from 60 to 90 centimeters. When you are playing cricket, we generally use this particular method. We will ask the chotu of the team, chotu, you come, take 22 steps, sir, and place the steps. I'll give you first batting and bowling, we will say. But we never give him batting and bowling. Okay, yes. So that is a very good example of pacing. But where in surveying we use this? In surveying, I use this during my reconnaissance work. I use this during my reconnaissance work. Okay? Like reconnaissance means nothing but site visit. So when we are going for site visit, it is not important for me to get accurate values. Approximate values are more than sufficient for me. For that, this particular pacing method will help me. That's it. Okay, right. Now next step, to make this particular pacing a little bit easier, I have a passometer. What the passometer will do is, it will count the number of paces for you. It's a small instrument. You can put this instrument in your pocket and you can walk around. Every time you take a step, what will happen? Every time you take a step, what will happen? Right, your body will vibrate, and each vibration will be counted as a pace. Each vibration will be counted as a pace. That is what we call it as, passometer. Now you multiply with the average value of your pace, you'll get your distance. Now a much more advanced version of this is what we call it as speedometer. It is an electronic instrument, it's a digital instrument. This is what you have in your smartwatches, in your fitness bands. So what this device will do is, you see, it counts the number of paces and multiplies it with the average pace time. So when you turn on your fitness band and you run for like 1 hour, they'll say, today you have taken some 5,000 steps, you have completed 2.5 kilometers, something like that. They'll say. Correct? Yes. So that is the pedometer working. It's not very accurate, it is approximate only. Yes. Right. Now, the last method of linear. That is correct? Yes. So that is the pedometer working. It's not very accurate, it is approximate only. Yes. Right. Now, the last method of linear measurement is what we call it as, the next method is what we call it as by using a measuring wheel, odometer, and a parameter. So, right, this is very useful in curved surfaces. Basically, this instrument consists of a wheel like this, okay, right, and it is having an odometer attached to the center, and it will be also having a handle like this. Whenever I move this particular instrument, the wheel will rotate like this. Whenever I complete the rotation, the odometer will count it as 1, 2, 3, etc. If I know the perimeter of this particular wheel, and if I know the number of rotations it has done, what will be my distance? Number of rotations multiplied with the perimeter of the wheel. That's it. So if you have rotated 10 times, the perimeter of the wheel is 1 meter. What's the total distance you covered? Total distance you covered is 10 meter. That's it. So this is useful in curved surfaces. This measuring wheel and all is used in curved surfaces. In your metro construction sites and all, you'll be able to see this. Right? This instrument is the odometer. This instrument is the odometer that counts the number of rotations. So every time the wheel rotates, this dial will keep on changing. That is the odometer. It shows the number of revolutions made by the wheel. That's it. The last discussion is regarding our speedometer. So this is what we use in our vehicles. So the odometer. It shows the number of revolutions made by the wheel. That's it. The last discussion is regarding our speedometer. So this is what we use in our vehicles. So we have a dial like this that shows the speed, and here we'll have a dial like this that shows me some values like this. So what is this value shown? It is nothing but the distance traveled in kilometers. What is that value shown? That value shown there is nothing but the distance we have covered in kilometers. So it shows you the speed. It shows you the speed as well as right the distance covered in kilometer. Okay, it shows you the speed as well as the distance that you have covered in kilometer. That's why we call it as a speedometer. That is why we call it as a speedometer. Okay, that's it. So we'll stop here for today, right? Yeah, we finished the chain surveying chapter. So now, this was we started actually the chain surveying chapter, and this was the last discussion that we had. Okay, approximate measure. Yes or no? Yes. So let us continue our chain surveying chapter. Yeah. So remember, we are going to discuss about the first basic measurement, which is nothing but the chain survey. First basic measurement, which is nothing but the horizontal distance. Horizontal distance is given by the instrument known as chain. Therefore, we call it as chain survey. Right. So we discussed about the different methods of linear measurements. Okay. We discussed about the different methods of linear measurement. Right. They are direct distance measurement, optical distance measurement, electronic distance measurement, and finally we have approximate. Can you please tell me, out of the 4 methods, where does chain surveying fall in? Can you tell me? Out of the 4 methods of linear measurement, in which method will chain surveying fall in? Chain surveying will fall in which method? It will fall in the method of direct distance measurement. Okay. Yes, very good. So chain surveying falls under direct distance measurement. Yes. So how can I define our chain surveying? Yes. So we'll start our discussion on chain surveying. Chain surveying is part of direct distance measurement. So how can I define my chain surveying? Please understand, chain surveying can be defined as the branch of surveying that deals with only linear measurement and no angular measurements are taken. What is chain surveying? It is the branch of surveying that deals with only linear measurements and no angular measurements are taken. Okay, that is how we can best define our chain surveying. Okay, please read the statement. It's a branch of surveying that deals with only linear measurements and no angular measurements are involved. That is how we can define it. Yes. Now, where is chain surveying suitable? Is chain surveying suitable for every type of ground condition? The answer is no. Chain surveying is only suitable for very flat terrain, right? Fairly leveled ground, we can say. So fairly leveled means what? The ground is having almost the same uniform elevation. If the ground is highly undulated, chain surveying is not really suitable. Okay. So please remember, chain surveying is suitable for fairly leveled grounds and open grounds with few simple details to be plotted. If your ground is having so many details present, for example, there are so many buildings, so many water bodies are there, or so many, let us say, forested areas are there, then chain surveying is not really suitable for us. Yes. So this should be identified by the surveyor during the reconnaissance. Okay. When the surveyor goes out for reconnaissance work, initially, he should be able to identify that can we do chain surveying there or not. Yes. Right. Now, So during the reconnaissance itself, the surveyor should be able to say, right, whether we can do chain surveying there or not. Okay, that's it. Now let us talk about the principle of chain surveying. What is the principle of chain surveying? In one single word, I can say the principle of chain surveying is nothing but chain triangulation. The principle of chain surveying is nothing but chain triangulation. What is the meaning of chain triangulation? See, the term means that the entire area that is to be surveyed, it has to be divided into network of triangles. The principle of chain surveying is chain triangulation. What is the meaning of chain triangulation? The entire area that is to be surveyed, that has to be divided into network of triangles. What kind of triangles? Well-conditioned triangles. Okay. So you cannot divide the area into whatever triangle you want. You have to make sure the area that is, the triangles that we are forming, those triangles are well-conditioned triangles. So when will I call a particular triangle as well-conditioned? See, I can call a triangle as well-conditioned triangle if no angle in the triangle is too acute, right, and no angle is too obtuse. No angle is too acute and no angle is too obtuse. Okay, such a triangle will be known as well-conditioned triangle. What do you mean by acuteness? Less than 90 degree. What do you mean by obtuseness? Greater than 90 degree. So what is the limit of acuteness that we kept? 30 degree. What is the limit of obtuseness we have kept? That is 120 degree. Okay. So whenever we are having triangles where the angles are lying between 30 and 120 degree, such a triangle has to be called as a well-conditioned triangle. So you read the principle. The entire area to be surveyed is divided into network of well-conditioned triangles. What is the meaning of well-conditioned triangles? Okay. The meaning of well-conditioned triangle is a triangle in which no angle is too obtuse or too acute. And the limit of acuteness is kept as 30 degree and the limit of obtuseness is kept as 120 degree. Based on this, there was a few gate PYQs. Based on this, there was a few gate PYQs. So recently in GATE 2020, they asked a question like this. The following triangles are given, triangle PQR. Okay, the angles of triangles PQR are given. They ask you which of these triangles are not suitable for surveying. Which of these triangles are not suitable for surveying? How do you know? See which of the triangles are having angles greater than 120 degree, less than 30 degree. Those triangles are not suitable for our surveying work. Understand? So based on that particular concept, there was a previous year GATE 1 mark question for us. Yes. So this is the definition of chain surveying under the principle of chain surveying and the condition of well-conditioned triangle. Right. Now we need to talk about the different terminology. Definition of chain. Surveying, use in our chain surveying work. What are the different terminologies that we use in our chain surveying work? Okay, we start with our first terminology, that is what is meant by main survey stations. Okay, right. Look at the definition here. Main surveying stations are prominent points which are identified around the area to be surveyed. What are main survey stations? They are nothing but prominent points. Prominent means permanent, fixed points which are identified around the area where we want to do our survey. Okay. Let me explain that particular point here. So you imagine that this which the area around which we need to do our chain survey. We are having an area like this. We need to do our chain surveying around this area. Before any sort of survey can happen, what is the first job we need to do in the field? That is obviously nothing but reconnaissance. So the surveyor will come to this particular field, and what he will do? He will walk around the area to be surveyed. Okay. The surveyor will come to this particular field, and he walks around the area, and he has to identify some fixed reference points around the area to be surveyed. So let us assume that here he has identified a place of worship. What is point A? Point A is nothing but a place of worship. It can be a temple, it can be a church, it can be a mosque, anything. Right. Now, this particular place of worship is a permanent point. Correct? It's in transportation engineering and all, we call such places of worship and all as obligatory point. We have certain obligations towards it. Practically meaning is that we should make sure that these points are not disturbed. That is the basic idea. Okay. So that particular point A is a place of worship. It remains fixed. Nobody generally disturbs such points. He continues to walk around the area, and let us assume that he reaches another point here, say B, where he has identified, let us say, a railway station. So railway station is also a public building, a public infrastructure, and generally they remain fixed. Correct? Nobody is going to change the position of railway station right in a year or so. No, it remains fixed for very long periods of time. So it's a public infrastructure, a building that is going to remain fixed. Yes. He continues to walk around the area, and let us assume that when he reaches this particular point here, say C, he has identified, let us say, a 220 kV substation. He has identified there is a small 220 kV substation is there. So these are also fixed points. Substations and all cannot be moved because of the heavy wirings that we have done. So it also remains fixed. And similarly, he walked around the area finally to come to this point D. What is D? D is nothing but another fixed point of reference. Say something like our say a government office, for example, the collectorate. Okay, right. For example, the secretariat. So these points are also remains more or less fixed. So such fixed points of reference which are identified around the area to be surveyed, that is what we call it as our main survey stations. So basically, they are the reference points for us, control points for us. Yes. So if you understand what is the main survey stations, can you tell me what are the lines joining the main survey stations? Join the lines like this. What do we call these lines as? We can call these particular lines as main survey lines. Lines joining the main survey stations are main survey lines. Okay, so that is the next terminology. Right, what is meant by main survey lines? So survey lines joining the main survey stations are what we call it as our main survey lines. That's it. Now comes the most important terminology, number 3. What is meant by baseline? What is meant by baseline? Okay, this is the most important terminology. See, baseline is nothing but the chain length that is passing through the center of the area to be surveyed. What is our baseline? Chain length that is passing through the center of the area to be surveyed. So please try to recollect. When you are doing chain surveying in your college, right? You go to your lab. The teacher will give you some, teacher will give you one chain bundle. You take the chain bundle and you go to the field. Now in the field, the lab assistant might have already kept a number of ranging rods in the field. Right? They have already kept a number of ranging rods in the field. What we need to do is we need to extend that particular chain to the center of all the ranging rods. If you remember, you will untie the chain bundle and you throw the chain to the center of all the ranging rods. This chain length that is passing through the center of the entire ranging rods is what we call it as our our baseline. Okay. So that particular ranging rods in your college, right, or in your experiment in your field, they are the control points. But when we do the actual survey in the field, right, they don't put ranging rods. We have this particular reference points in the field. Okay, right. So what is the baseline? Chain length passing through the center of the area. If you look at this figure here, we can either take it along the direction of AC or we can take it along the direction of BD. So please tell me, will I take it along the direction of AC or will I take it along the direction of BD? In which direction do you think I'll take my baseline? Please remember, baseline should always be taken along the longest direction. Okay. So in this figure, if I consider BD and AC, obviously AC is the longer line. Yes or no? Yes. So baseline, or else I can also call it as the chain line, has to be taken to the center of the area. Has to be taken to the center of the area to be surveyed, and the longest line is identified. So who is the longest line here? I will say AC is the longest line here. So let me draw that here. Okay. That is the baseline passing through the center of the area to be surveyed. So if you look at this, I have represented my chain line and our main survey lines as completely different. This dotted line of representation is what we generally use for our chain line. Yes. So how many terms we have defined so far? We have defined 3 terms. Correct now. main survey stations, main survey line and baseline. Now, after taking these three terminologies, please look at the area. Tell me what happened to the area. After taking these three terms, what is happening to my area to be surveyed? You will realize that the area to be surveyed is divided into network of triangles. Correct? If you look at this, you will realize the area to be surveyed is now getting divided into network of triangles. This procedure is what we call it as chain triangulation. This procedure is what we call it as the chain triangulation. The entire area to be surveyed is divided into network of triangles. Yes. So now that the triangles are formed, what we need to do is we need to check the framework of triangles. We need to check the accuracy of framework of triangles. For that, we will introduce check lines. Right? So the next line that we need to discuss, terminology we need to discuss is what is meant by check line. Check lines or proof lines, they are used to check the accuracy of the framework of triangles, whether the framework of triangles formed are correct or not. Right? For this purpose, we use our check line. Please understand, you can take a check line in whatever direction you want. If you want, you can take a check line like this. If you want, you can take a check line like this. No problem. If you want, you can take a check line like this. If you want, you can take a check line like this. In whatever direction you want, you can take your check line. But make sure that for every triangle formed, there is at least one check line. For every triangle formed, there is at least one check line. Okay. So that particular point has to be remembered. Right. For every triangle formed, there should be at least one check line. So what I'll do is, I'll take a common check line for both the triangles. Here we are having two triangles here, ABC and ADC. For both of them, what I can do is I can take a combined check line, something like this. You can take a combined check line, something like this. Right. So that's the combined check line that will help me check the accuracy of my work. Okay. Right. So that is a combined check line. So we have baseline, right? We have check line. So we divided the entire area to be surveyed into network of triangles. We check the accuracy of framework of triangles. We check the accuracy of framework of triangles. Now, can we work from whole to part? Yes or no? The boundary conditions are identified. The boundary conditions are checked. Now, can I work from whole to part? Absolutely yes. So this is the principle of survey. First, you establish the boundary conditions, check the framework of boundary conditions. After that, you can start plotting the details inside the area. Okay. So here, what we have to do is we need to plot the details present inside the area to be surveyed. Okay. So let us see what we can do for that. You imagine that inside this particular area, you are having a building like this. Inside this particular area, you imagine that there is a building like this. You imagine that you are having a building like this. So this is a building that we are having. Okay. So there is a building like this. What we need to do, we need to plot the position of this particular building. So to plot the position of this particular building, what are the measurements we take? The measurements we take is what we call it as offsets. Okay. So what are offsets? Offsets are nothing but lateral measurements taken from chain line in order to plot details. Okay. In order to plot details. So to plot the position of this building from the chain line, I need to take lateral measurements. Okay. Right. Lateral means towards the left or towards the right. I need to take measurements. Okay. So this particular measurements can be taken in two ways. Okay. So you see, to plot this particular corner of the building, if I want, I can take an offset like this. If I want, I can take an offset like this. Okay. So this particular offset, I call it as JK. Right. Right. What is the angle it makes with the chain line? Look at the offset JK and tell me what is the angle the offset JK is making with my chain line. It is making an angle other than 90 degree. It does not make 90 degree. So we can call this particular offset JK as a oblique offset. I can call that particular offset as an oblique offset. Right. But if I put an offset exactly at 90 degree to my chain line, right? In order to plot the other corner here, if I am putting an offset exactly 90 degree to my chain line, exactly at 90 degree to my chain line like this, right? What we call it as? We will call it as a perpendicular offset. We will call it as a perpendicular offset. So like this, if I am putting an offset that is exactly 90 degree to my chain line, right? What do you call this offset as? GH. I call that offset as GH. That is a perpendicular offset. So JK is known as my oblique offset, right? Because it is not at 90 degree. And the other offset, GH, is what we call it as a perpendicular offset. So what we call it as a perpendicular offset. So offsets may be either oblique or offsets may be perpendicular. Okay. Offsets may be either oblique or it may be perpendicular. Okay. 1 second. Okay. Let me make this a little bit neater. So, what kind of offset is that? That is a perpendicular offset, GH. And if I'm putting an offset like this, like it is making an angle other than 90 degree. So JK is now known as the oblique offset. JK is the oblique offset, and GH is the perpendicular offset. So we have perpendicular as well as oblique offsets. Yes. Right. Now, based on length, we have two types of offset. Right. They are short offsets. Based on length, we have short offset and we have long offsets. Whenever the offset is less than 15 meter, we call it as short. Whenever it is greater than 15 meter, we call it as long offsets. Okay. Now, out of short and long offset, which one do we prefer to have in the field? Do you prefer to have a shorter offset or do you prefer to have a longer offset? Please remember, we always prefer a shorter offset because, right, if the offset is not set out exactly in the direction that we want, for example, you imagine you want to put a 90-degree offset. Okay, the offset is supposed to go exactly at 90 degree, but due to some error, the offset is going at an angle not equal to 90 degree. So the correct offset should go in this direction, but due to an error, the offset is going in this direction. Now, if the distances is more and more and more, this error keeps on increasing. Correct now. The error between the correct direction and the incorrect direction keep on increasing if the length of the offset is increased more and more and more. So generally, we don't want that to happen, so we keep that particular offset as short offsets. That's it. But do you really think that every time we'll be able to put only short offset? No. What if we are having a detail far away from the chain line? You see, there is another building here that is very far away from the chain line. So if I try and plot that particular offset here, it would be what? It would be nothing but a long offset. So to avoid this, what will I do? Is I'll take my next terminology here. That is number 6. That is known as a tie line. Okay. So here the problem we are facing is the detail is very far away from the chain line. So in order to plot that particular detail, right? In order to plot the detail by using a short offset, what I will do is I will run a line like this. Right? I will run a line like this very close to the detail to be plotted. I'll run a line like this very close to the detail to be plotted. What is this line known as? This line is what we call it as a tie line. This line is what we call it as a tie line. Guess what is this? This is P. This is Q. Okay. So what is this particular line here known as? This line here is what we call it as a tie line. Okay. So now tell me, if I want to plot the particular details, what I need to do? I need to put a short offset from where? From this particular tie line. I just need to put a, you see, this is a short offset from this particular tie line. That's it. So what is this line PQ known as? Tie line. What is the station P and Q known as? Station P and Q are known as subsidiary survey station. Okay. What is stations A, B, C, D? Stations A, B, C, D are known as main survey stations. Stations A, B, C, D are known as main survey station, but stations P and Q are known as subsidiary survey stations. That's it. So these are the different terminologies involved in our chain survey. So please remember, what is the first terminology? What is meant by the main survey stations? Right? What is meant by main survey stations? What are they? A, B, C, D. They are prominent points identified, fixed points identified around the area to be surveyed. What are the lines joining them? The lines joining them are main survey lines. Okay. The lines joining them are main survey lines. A, B, B, C, C, D, etc. Yes. Now, what is meant by baseline or chain line? Baseline or chain line represents the chain length, the actual chain line that is passing through the entire area to be surveyed. Right, passing through the center of the area to be surveyed. Longest line should be taken as the baseline or chain line. Yes. So once you take these three terms, the area to be surveyed is divided into network of triangles. This is what we call it as chain triangulation. Right. Now to check the accuracy of the framework of triangle, we'll take another set of lines, what we call them as check lines or proof lines. The check lines or proof lines are used to check the accuracy of framework of triangles. Check lines or proof lines are used to what? To check the accuracy of framework of triangles. Yes. Right. Now at least one check line should be there for every triangle formed. After that, what do? You try and plot details inside the area by taking offsets. Offsets are lateral measurements, left and right measurements taken from the chain line in order to plot details. They can be perpendicular offset like GH or oblique offsets like JK. Based on length, we have short and long offsets. Right? We generally prefer to have a shorter offsets because the error in plotting is reduced if you take a short offset. But if a detail is very far away from the chain line, to avoid taking long offsets, we take a tie line very close to that detail. In that figure, the tie line is PQ. Right. So from this tie line, I can put my short offsets to plot the building there. Now the tie line is run between the stations P and Q. These stations P and Q are known as subsidiary survey stations. That's it. So these are the different terminologies involved in our chain surveying work. Let us just read about them. So what are main survey lines? Main survey lines are nothing but survey lines joining the main survey stations. Yes. What is meant by baseline? Baseline is nothing but it represents the chain length passing through the center of the area to be served. Always remember, it is the longest line. It is the longest line only. So we have divided the area into triangles. Now we need to check the accuracy of framework. So check lines are used to check the accuracy of the framework of triangles. Okay, they are also known as proof lines. Okay, they are also known as proof lines. Next step, we have also the accuracy of the framework of triangles. Okay, they are also known as proof lines. Okay, they are also known as proof lines. Next step, we have offsets. What are offsets? Offsets are nothing but lateral measurements taken from survey lines in order to plot details. In order to plot details. Okay, they may be per perpendicular, right? Or they may be oblique. Based on length, we have short offsets less than 50, long offsets greater than. That's it. Okay. So that is our offset. Now, next one is what is meant by tie lines. Right. If we have short offset. Offsets less than 50, long offsets greater than 50. That's it. Okay. So that is our offset. Now, next one is what is meant by tie lines. Right. If a detail is very far away, we plot them like this. They are run very close to the details to be plotted in order to avoid taking long offset. Yeah. Right. And they are running in between the subsidiary survey stations. They are running in between subsidiary survey stations like P and Q. Right, that's it. Now, one more terminology I would like to discuss here, that is, what is the meaning of chainage? Chainage is nothing but the distance measured along the chain from the starting point. So you imagine that this is the starting point of our chain. I call it as zero meter. Okay, right. So right, the chain is going like this. The chain is going like this. Right. So that is the direction in which our chain is going. Right. So now you imagine that, right, at this particular point here, I am having a perpendicular offset of say 5 meter. I am having a perpendicular offset of 5 meter. So how do you express the position of this 5 meter offset? What you do is you start from this 0 meter and you measure up to this particular point. So let us assume that this is a 10 meter mark. Let us assume that this entire distance is 10 meter. So this particular 10 meter is what we call it as chain inch. So I can write like this: at 10 meter chain inch, at a 10 meter chain inch, right, we have 5 meter offset. At a 10 meter chain inch, we are having a 5 meter offset. That is the understanding. So what is chain inch? Right, it is the distance measured along a chain from the starting of the chain. So this is what we call it as chain inches. Okay. So when I say chain edge of a point is 1000 meters, from where the chain started, we measured along the chain and we got a distance of 1000 meters. So that distance is what we can call it as chain edges. Okay, yes. So these are the different terminologies involved in our chain survey work. That's it. Okay. Now we will talk about the instruments used in chain survey. What are the different instruments we are using in our chain survey? What is the first and foremost instrument? No doubt, the first and foremost instrument is nothing but the chain. So let us see how does the chain looks like and what are the details of the chain. Okay, so just give me a second. Okay, so let us see how does our chain look like and what are the details here. Okay, so let us see how the handle of the chain looks like. So basically the chain is made up of a handle that is made up of brass. It looks like this. Okay, right, and at the center of this particular handle we will be having a, right, the center of this particular handle will be having a groove here. Okay. So this is the handle that we are having. Okay, this is the handle that we are having. It is made up of brass. Okay, draw that again. So we are having a handle like this. This is made up of brass. We call it as the brass handle. And whatever is the length of the chain, that length of the chain will be engraved on this particular, brass handle like this. If it is 20 meter, it will be written as 20 meter. If it is 30 meter, they will write it as something like 30 meters. Okay. So whatever is the length of the chain, that length is engraved here like this. At the center of this particular brass handle, we provide a groove here. The center will be providing a small groove here. You will also see that groove. Yes. Now, from this particular point, the chain will start with a joint here. So this joint is known as a swivel joint. What we call this joint as? This joint is what we call it as a swivel joint. It will allow the chain to rotate without getting twisted. Right? That is the swivel joint. And from the swivel joint, the chain material will start. The wire will come like this. It is made up of 4 mm diameter mild steel wire. It is made up of 4 mm diameter mild steel wire. It comes like this, form a groove, followed by one oval shaped ring will come, followed by one circular ring will come, followed by another circular ring will come, another oval shaped ring will come, right? And then, right, we form a groove like this and we can continue. So this is how the chain is supposed to look like. Okay. Now, the distance measured from the outer end of the handle to the center of the first vertical circular ring. What is this? This is what we call it as one link. This is what we call it as one link. So from the center of the first circular ring, vertical circular ring, to the outer edge of the handle, that is what we call it as the first link. Okay, right. So in metric chains, please remember, what do you mean by metric chain? Metric chain means chains that come in definite fixed meter length. What is the value of one link? Value of one link is going to be how much? 20 centimeters, or it is equal to 0.2 meters. Right. So that is our, one link in a chain. That is the one link in a chain. Right. Now, my 20-meter chain will contain how many such links, sir? You can do 20 by 0.2. It will turn out to be 100 links. It consists of 100 links. And 30-meter chain consists of how many links, sir? 30-meter chain consists of 150 links. 30-meter chain consists of 150 links. Of 150 links. Okay, that's it. Now, are there any graduations in my chain? For example, if you take a tape, okay, if you take a steel tape or any other tape you take, right? If you observe in this particular tape, you can always see that there are some graduations engraved. So my question is, do you have any such graduations in our chain? The answer is no. We don't have any such graduations in our chain. Right? Then how do I know the distances completed? The distances completed is calculated by using our markings. So we provide generally some markings. What are the markings that we do? Let us try and understand. Remember, at every 1 meter interval, we provide brass rings. Okay, so the chain is 4 mm diameter mild steel wire. I told you the material used to make the chain is 4 mm diameter mild steel wire. Now, this particular mild steel has a metallic gray finish, right? But what we do is, after every 5 links, 5 link means 1 meter. 5 link means 1 meter. So after every 5 links, we provide a brass ring. So this particular brass ring is golden in color, so it can be easily identified like this. So when you provide a brass ring on the metallic gray surface, we can easily able to identify. Okay, right. Now similarly, at every 5 meter intervals, what we provide a tally. At every 5 meter intervals, what we provide is a tally. So let us see how the different tallies will look like. See, our 5 meter tally will look like this. Right, 5 meter tally looks like this. It is having one teeth. How does the 10 meter tally look like? The 10 meter tally looks like this. 10 meter tally will look like this. Okay, it is having 2 teeth. And how does the 15 meter tally looks like? The 15 meter tally will consist of 3 teeth like this, 1, 2, and 3. So 15 meter tally consists of 3 teeth like this. Okay, so remember, from whenever you see this 10 meter, the meaning is this tally. The meaning is from where you started, you have completed 10 meters. You see this tally from wherever you started, you have completed 15 meter, and this will indicate from the starting point you have completed 5 meters of length. That's it. So if so, how does how many 5 meter tallies will be there in my 20 meter chain? How many 5 meter tallies will be there? How many 10 meter tallies will be there? And how many 15 meter tallies will be there? Okay, in my 20 meter chain. Okay, so please remember, we are going to provide these tallies in symmetrical manner. In a symmetrical manner, from the center line, we need to make sure that in a symmetrical manner these tallies are provided. If so, how many 5 meter tallies we will see? Right? Please remember, we are going to see 2 5 meter tallies. We are going to see 1 10 meter tally, and we are going to see 0 15 meter tallies. We are going to see 0 15 meter tallies. Okay. So this is going to be the tally arrangement. This is going to be our tally arrangement. Let me explain why. As I told you, we are going to provide it symmetrically. So if this is my 20 meter chain, right? This can be 0 meter, this can be 20 meter, or if somebody wants, they can start from here as 0 meter and end up here with 20 meter. So for a person starting from this end, for a person who's going from this end, after 5 meter, he should see 5 meter tally. After 10 meter, he should see 10 meter tally. After 15 meter, what will I put? Will I put 15 meter? No, I should put 5 meter. Because if I put 15 meter tally here, the person coming from this side will get confused. So to avoid it, we provide it symmetrically 5 meter tally. Similarly, in my 30 meter chain, how many of these tallies will be there? From both ends. How many 5 meter tallies will be there? 2. From both ends. How many 10 meter tallies will be there? 2. Right. From one end I can measure 10 meter. The other end also I can measure 10 meter. And 15 meter tally will be exactly at the center. Yes. So there is 1 15 meter tally. In the same sense, how many tallies will be there in the 40 meter chain? Can you tell me? How many tallies will be there in my 40 meter chain? Right. 0 0 0. Because there is no 40 meter chain. Don't think too much. There is no 40 meter chain. Okay. There is only metric chains coming in 20 and 30 meters. There is also 5 meter chains, 10 meter chains, etc. But for all our engineering works, we will go with the 20 and 30 meters only. Yes. So that is the details regarding the chain. Right. Now there are some standard dimensions of the chain that you can remember. Okay. There are some standard dimensions of the chain that you can remember here. These are the different types of chains we use in our chain surveying work. Right. The first one is what we call it as metric chains. They are coming in definite meter length. 10 is there, 20 is there, 30 is there. But generally we use 20 and 30. So if you look at that, what is the value of one link here? One link is equal to 20 meters. Right. The next chain that we have is what we call it as a revenue chain. The next chain we have is what we call it as a revenue chain that is around 33 feet long. Okay. 33 feet long, consists of 16 linker. What is the value of each linker? 33 divided by 16, you will get it as 2 and 1 by 16 of a feet. Remember, 1 feet is equal to how much? 0.3048 meters. 1 link is equal to how much? Sorry, 1 feet is equal to 0.3048 meters. So 33 feet means 0.3048 into 33, you will get it as 10.06 meters. Okay, right. The next chain is what we call it as Gunter's chain. What's the name of the chain? Gunter's chain. Okay. One student told me, sir, Guntur chain. Right. There is no Guntur, Hyderabad, Vijayawada chain, nothing like that. Guntur is a district in, I think, in Andhra Pradesh. Okay. So he remember that name and he said, sir, Guntur chain. So Guntur chain, it is Gunter's chain. Okay. Not Hunter, Gunter. Okay. Gunter's chain. And if you look at this, it is exactly twice of the revenue chain. It's exactly twice of the revenue chain. Exactly 66 feet long. 10.06 into 2, 20.12 meters. But it contains how many links? 100 links. What will be each link? 66 feet divided by 100. Right. This chain is also what we call it as surveyor's chain. Next we have the engineer's chain. Engineer's chain is 100 feet long, consists of 100 link. 100 feet means how many meters? 30.48 into 100. Sorry, 0.3048 into 100. 0.3048 into 100. You will get it as 30.48 meters. The last kind of chain that we have is known as a steel band chain. See, the first 4 chains that we discussed. These 4 chains that we discussed, these are known as linked chains. Why we call them as linked chains? Because they have that link arrangement, right? They have this kind of link arrangement. So no, that is why we call them as linked chain. The advantage of providing this 3-ring arrangement is that it gives us a lot of flexibility. But the disadvantage is if you pull it too hard, what is going to happen is the rings will open up like this. If you pull too hard, the central ring can open up like this, or any other ring can open up like this. So accuracy is not that very high. So to solve this problem, we have introduced the steel band chain. Now the advantage of this steel band chain is that it is more accurate. So it is a continuous strip of steel. Just like a ribbon band, we have a continuous strip of a steel. Okay, correct. Now in this particular strip, we have our graduations and all mentioned there. We can use it to take measurements very accurate. But the problem is, you see, right? If this particular chain breaks in the field, if it gets broken into two pieces, there is no way we can repair it in the field. I need to take it back to the workshop, weld it, then only I can fix it. But our linked chains now, we can easily fix it in the field. If the rings are getting open up like this, what do? Take a plier and plus it together. What happens? It becomes back to normal. So field repairs are possible only with the linked chain, which means our work can be taken uninterrupted. Please understand, steel band chain has advantage, but it also has disadvantages. They come in different length of 20, 30 meters, etc. etc. Yes. So these are the different types of chains that we have. Gate people simply ignore this. Gate students, you can simply ignore this because it is not a very important discussion for you. It's not a very big important discussion for you, right? If you are writing gate examination, but for other examinations like ESC, okay, right, prelims followed by our PSUs, right, followed by our PSC, followed by our SSC, followed by our RRB. For all these examinations, this particular information is important. In fact, around in the last February, there was a TSPSC examination, Telangana PSC examination. So in survey, they asked around 12 to 15 questions right, every time. And out of this 12 to 15 questions, 3 to 4 questions was from this discussion, from this chain only. This details, whatever numericals are represented here, numbers are represented here. Based on this particular slide here, they asked 3 to 4 questions. Okay. So in PSUs and PSCs and all, you can see this. Not too much in gate and not very, very important for ESC also, but still they can ask you. In ESC prelims and all, they can ask you. Yes. For those kind of examinations, you please right. Next up, we will talk about the testing of chain. Chain is the most important instrument in our chain surveying, obviously, as the name suggests. So we need to know what are the testing conditions for our chain. Whenever any product is made in our factory, any product, okay, is made in our factory, before we can actually use it in our field, we need to do our field test. Correct now? We need to do our testing. Okay, right. We need to do something known as quality control and quality assurance. QA/QC we need to do. So just like that, the chain, before I can use it in the field, I need to test it, or rather I should standardize the chain. Right. So what we need to discuss is, we need to talk about the testing or standardization of chain. So we need to make sure that we are having a standard chain in the field. Okay, right. So we need to take the chain and test it. What are the testing conditions for a chain? Please remember this testing condition. A chain is tested under a temperature of 20 degrees Celsius. A chain is tested under a temperature of how much? 20 degrees Celsius. And a pull of how much? You see, tested under a temperature of 20 degrees Celsius. And a pull of how much? 8 kgf. What do you mean by kgf? Don't say Rocky by. Right? Don't say Rocky by, okay? It's not Rocky by kgf. It is kilogram force. Can you convert this into Newton? Yes, 80 Newton. Just to multiply that with gravity. Take gravity value as 10, you'll roughly get it as 18 newtons. So this is the standard testing condition for a chain. Remember it. A chain is tested under a temperature of 20 degrees Celsius and a pull of 8 kgf or 80 newtons. So when I do this, what should be the condition? What should be the performance of the chain? Please remember, every meter length of the chain should be within plus or minus 2 mm. That means when you give the chain this particular condition, no single meter length should vary by more than 2 mm. Right, should not vary by more than 2 mm. Now, what is the maximum change allowed in a 20 meter chain? Right, the maximum change allowed in a 20 meter chain is plus or minus 5 mm. So the 20 meter chain should be 20 meter. It should be 20 meter plus or minus 5 mm. So the maximum change allowed in the 20 meter chain is 5 mm. Right, allowance for 20 meter chain is 5 mm. And for 30 meter chain, it should be 80 mm. Sorry, 8 mm. Right. So it should not vary by more than 8 mm. Right. Now it looks very easy to understand. But please tell me, when I am applying a pull of 80 Newton, when I am giving a pull of 80 Newton, when I am giving a temperature of 20 degrees Celsius, how can we write minus 5 mm? How can the chain be 20 meter minus 5 mm? Plus 5 mm is okay. We are pulling it, length should increase. But then how minus 5 mm? Minus 8 mm is justified. Can you imagine? Plus 5 mm and plus 8 mm is justified because we are giving a pull. But under a pull, how can the length of 20 meter be less than 20? How it is possible to have 20 minus 5 or 30 minus 8? Because please understand, if you simply take your chain bundle, 20 or 30 meter chain bundle, simply extend it and put it on the ground, is it equal to 20 meter or 30 meter? My question is, under zero pull, is the length of the chain equal to 20 or 30? The answer is no. If you don't apply any pull, the chain length is not equal to 20 meter or not equal to 30 meters. It will always be less than 20 or 30 meter. Until and unless you apply a pull, the chain will not be fully stretched up. Okay, chain needs to be fully stretched up. Right, under zero pull, the chain will not be stretched up, so it will not be equal to 20 meter. So when we apply a standard pull of almost 8 kgf, right, or 80 newton, the chain should be get stretched up fully and ideally should increase up to 20 meter. Correct? Right, ideally it should increase up to 20 meter. That is ideal case. Right, now the allowance given is plus or minus 5 mm for 20 meter. That means it can be more than 20 by 5 mm, or after stretching it can be less than 20 meter by 5 mm. Already it is less than 20. When you apply the pull of 80 newtons and the 20 degrees Celsius temperature, the chain should be either equal to 20 or less than 20 by only 5 mm or greater than 20 by only 5 mm. That is the idea. Okay, that is the idea. That is our testing conditions for the chain. Okay, yes. So please try to understand. Right. So next we'll talk about our second instrument, that is nothing but tape. Can anybody please tell me in one single word what is the purpose of tape? Why do you need tapes? Anybody? Tell me why we need tape. Anybody come on, give me an answer. In order to know length of chain is correct. No. Measurement, obviously measurement purpose only in Gayatri. Don't say very general answers. You get accuracy in measurement. No, Teja. Accurate measurement, no. Kunal Rawat. No. We cannot bring chain. No. It's chain surveying. Na. Chain surveying means chain should be there. Okay. In your marriage function, will you go? You are saying that in chain surveying, we cannot bring chain. That is why we are bringing in tape. So it is same as saying that you cannot go to your marriage, so you are sending somebody else for your marriage. It is not work like that. Okay. Horizontal resistance. That's correct, Sharan Kumar. The correct answer is no. In some places, if you cannot take chain there, chain surveying is ruled out. You rule out chain surveying. Okay, Manish. Now the correct answer is given by Sharan Gaji. The answer is to measure offsets. Okay. Right. No, in water bodies and all, we don't do that. Okay. So the correct answer is the tapes are used to measure offsets. Okay. Please try to imagine. Once our chain is set along the direction of the baseline. Once the chain is put along the direction of the baseline, we will never move it. Okay, the chain is always set along the direction of the chain line. Once the direction is fixed, we will never move it. But what if you want to measure an offset? What if you want to take an offset at 5 meter chainage? How do you measure the offset? For measuring the offset, you don't take a chain. No, you will take the tape and measure it. So the baseline or the chain line will go along the direction of the baseline. Along this baseline, if you want to take offsets left and right, you will measure it by using your tape. That is the correct answer. Yes. Right. Now let us see what are the different types of tapes that we have. First type of tape is what we call it as a cloth or a linen tape. As the name indicates, it is made up of the cloth material. As the name indicates, it is made up of what? Cloth material. Okay. What is the problem with the cloth material? The problem is, let's see, even though they are very flexible, the cloth material is very flexible. Just think about your shirt. Okay. They are very flexible. But the problem is, they are not accurate. If I apply small pull, they will stretch it. If I apply big pull, it will break into two pieces. So this particular cloth or linen tape, even though it's flexible, it's not really accurate or durable in the field. So it is not really used. To increase that strength or to reinforce this particular cloth or linen tape, we will put some glass fiber into the tape. The resulting tape is known as glass fiber tape. So it is slightly stronger than the cloth or linen tape, but still not strong enough, still not accurate enough. So this tape is also not really used. So what we do? We will further reinforce the material by using small diameter metallic wire. We will further reinforce our material by using small diameter metallic wires, resulting in metallic tape. Right, but this problem with small diameter metallic wires is thermal expansion. Yes or no? Yes. Truly speaking, the first three tapes are not really suitable for our chain surveying boards. Okay, not really suitable for our chain surveying board. So the most commonly used tape that we have is what we call it as a steel tape. You might have seen this steel tape, yes or no? Yes. With our carpenters, with our masons, with our plumbers, you can see this tape. They will always carry this tape around their pocket. Yes or no? Yes. Right. Now, tell me, right, where do you see these particular people, the carpenters, the masons, the plumbers, etc. Where do we see them? We see them in a construction site. We see them in a construction site. Okay. Therefore, I can say that steel tapes are used in construction surveys. These are used in where? These are used in our construction survey, right? Steel tapes. But tell me, what is again the problem with the material steel thermal expansion? So, right, steel tapes are accurately used, right, for small scale works, small works we can use it. But wherever high accuracies are required, steel tape is not justified because temperature variations can create thermal expansion in the tape that can result into errors. To avoid this, what we'll do, we will make an alloy, right, that has very less coefficient of thermal expansion. What is that alloy known as? That alloy is known as Invar alloy, and the resulting tape is what we call it as Invar tape. So what is this Invar alloy? Right. What is this Invar alloy? The Invar alloy is nothing but the combination of two metals who are there. They are nickel and steel. Okay. Nickel is used for 36% and remaining 64% is used by steel. This is what we call it as the Invar alloy. The advantage of this particular Invar alloy is that the coefficient of thermal expansion of Invar is only 1/10 of the coefficient of expansion of steel. The meaning is that for a given temperature change, if steel expands by 10 centimeter, Invar will only expand by 1 centimeter. For a given temperature change, if our steel is expanding by 10 centimeter, Invar will only expand by how much? 1 centimeter. Understand? Yes. That is the advantage. So accuracy is high. But the disadvantage of this particular tape is that it is a soft alloy. It is a soft alloy. So if you don't handle this particular Invar tape with care, the alloy can be broken into two pieces. It's very easily broken into two separate pieces. So you need to handle it with care. You cannot use it for daily rough and tough work. You can use it only when specific requirement of accuracy is there. The best example is, right, in our geodetic survey, we are trying to measure baselines. So I'll write like this: baseline measurement in geodetic survey. It is used in baseline measurement in geodetic survey. Okay, that is our environment. That's it. Okay. Now for day-to-day rough and tough work, I'll use steel tape. For our high accuracy work, I'll use Invar tape. Then where will I use these three tapes? Have you ever seen a cloth or a linen tape? Yes, you might have seen with a tailor. Correct now? So if you go to a tailoring shop, right, around the tailor's neck, you can see one tape. That tape is nothing but your cloth or linen tape. Why do you need that tape? Why does the tailor need that tape? Because for him, flexibility is important. So when you go to this particular tailor, he has to take your dimensions now. Does he take your dimensions, your shoulder, your waist, everything by using a steel tape? No. He does not use a steel tape. What he'll use a cloth or a linen tape for flexibility. Right? But the problem is accuracy is less. That is why we need to go minimum 2-3 times for refitting with the tailors. That is the problem. Yes. Okay. So that is our second instrument used. Nothing but the tape. Yes. Next we'll talk about our arrows. So the arrows will look something like this. Okay, so they are made up of the same material as that of our chain. Okay, 4 mm diameter, mild steel wire. The same material that we use. Yes. Now, what is the purpose of an arrow? Can you please tell me? Anybody? What is the purpose of arrow? When I keep this particular arrow on the ground, right? Where what is the point it tries to represent? Anybody? Anybody? Locate boundaries. No, Manish. Not really. To fix state. Harikiran, please explain that statement. अगर area change से big हो तो not entirely. Arrow put करते हैं. Right. So you see this. Look at this particular field condition here. Yeah. Look at this field condition. So imagine that you are having a ground like this. Okay. And here there is a ranging rod say P, and here we are having a ranging rod Q. So this is a survey line PQ. Okay, this is a survey line PQ that you are having. Let me say the length of the survey line PQ is x of base meter, 120 meters. The survey line PQ is 120 meters. To measure this, I am giving you a 30-meter chain. To measure this particular survey line, I am giving you a 30-meter chain. Please tell me, can you measure the entire 120 meter at once? Impossible, not really. Chain is only 30 now, so you cannot measure the entire 120 meter at once. What you need to do is, we need to measure it in small parts. So first I'll measure from 0 to 30, right? Once that 30-meter chain is completed, the end point is represented by keeping an arrow there. The end point is represented by keeping an arrow there. So I'll take my arrow where the 30-meter ends, I'll keep my arrow there. Next, from 30 to 60, I'll measure where the 60-meter end comes now, where the end of the chain comes, I'll keep another arrow. And similarly, 60 to 90, I'll keep an arrow, and so on and so forth. So tell me, what is the point the arrow is representing? Arrows are used to represent the end points of chain link. Please understand. So this is the 30-meter mark, this is the 60-meter mark, this is the 90-meter mark. So please understand. Arrows are used to represent the end points of a chain link. So when I drew the figure of the chain, I told you in the chain handle there is a small groove. On the chain handle there is a small groove. What is the purpose of the groove? To accommodate the arrows. Understand? The grooves are provided in the chain handle to accommodate the arrows. Yes. So arrows are used to represent the end point of a chain link. That's it. Okay. Now apart from this, there is one more purpose of an arrow. Can anybody please tell me, in a given chain surveying work, how many people are involved? In a given chain surveying work, how many people are involved? Do you know? In a given chain surveying work, how many people are involved? Anybody? Yes, very good. 2 members are there. Very good, Harikiran. 2 people are there. Who are there? We call them as leader and follower. We call them as what? Leader and follower. So in every chain surveying work, there are 2 people involved, leader and follower. So let us see what happens. So to measure the survey line PQ, what initially happens is both the leader and follower will come to the point P. Leader and follower both will come to the point P. The follower will hold one end of the chain on the ground at the point P. The follower will hold one chain handle on the ground like this. What the leader will do is he will walk along this direction. He will walk along the direction. Once the 30-meter end is completed, the leader will keep the arrow here. The leader will keep the arrow here. Now what the follower will do? Follower will follow him and comes to this arrow. Right. Now again, the leader will walk like this. Once the 30-meter end is completed, he will keep the next arrow here. What the follower will do? Follower needs to follow him. But what he will do is, he will take this arrow from the field. He will take the arrow from this field, keep it in his hand, and then he will follow. Okay. Now again, the procedure is repeated. The follower is now at the second arrow. The leader will go towards the next arrow or the next chain point or the chain end. What the leader will do? Right. The leader will take this arrow and follow him. So tell me something. At any given point of time, right? If our leader wants to know how many chain length have been completed, if the leader wants to know how many chain length have been completed, what should the follower do? To understand how many chain length has been completed, what should our follower do? Please tell me. What should the follower do? He simply needs to count the arrows in his hands. Okay, right. So if the follower is having 2 arrows in his hand, it means he has already taken 2 arrows in his hands and kept it in his hand. So the number of arrows in the hands of the follower, right? Calculation obviously can. Right. See, the number of arrows in the hands of the follower will tell me the number of chain completed. Okay. So the moment the moment the follower takes this arrow, right? 1 chain length completed. The moment he takes the second arrow, 2 chain length completed. He takes the third arrow, how many? 3rd chain length completed. So the number of arrows in the hands of the follower will represent the number of chain length completed. That is another use of our arrows. So arrows are used to represent endpoints of chain length. They are used to represent the end of our chain length as well as, right? In Indian practice, 10 arrows will be provided for every chain length. That is a practice in India. So if you come to me and ask me for a chain bundle, I should give you a chain bundle. Together with that, 10 arrows I should provide to you. Okay, that is the practice we follow in India. Yes. Right. Now what is the second use of our arrows? Now the second use of our arrows is, you see, the number of arrows in the hands of the followers represent the chain length. Alright, like this. Number of chain length completed. The number of arrows in the hands of the follower represents the number of chain length completed. That's it. Okay, so that is the number of arrows that we have. Yes, that is a discussion regarding the arrows. Yes. Okay, so next instrument that we have is nothing but the wooden peg. So wooden pegs are just like our arrows. Where do I keep them? Just like our arrows, we drive them into the ground. We'll drive them into the ground. Just like our arrows, wooden pegs are also driven into the ground. But we know what does an arrow represent. Right? An arrow is representing the end of our chain. Yes or no? Yes. Then if I see a wooden peg on the ground, what does it represent? What will a wooden peg represent? So if you remember, if this is our chain line, this is the ranging rod here P, this is the ranging rod here say Q. Okay, so this is Q point, this is P point. Okay, so whenever there is end of chain coming now, we will keep them as arrows. Okay, but where do I keep my wooden pegs? You imagine I am trying to remove the position of this ranging rod. My length is completed. My PQ length measurement is over. Now, my PQ length measurement is over. Now I need to remove the ranging rods from the points P and Q. Once the position of the ranging rod is removed, will I keep an arrow there? No, you're not supposed to keep an arrow there. You need to drive your wooden pegs here. You need to drive your wooden pegs. Please remember, wooden pegs are used to represent relatively fixed points. See, when I measure the length of the line PQ, after that arrows are not required. I'll remove the arrows from the field. Right, the follower keeps on taking the arrows from the field. So as soon as PQ length is measured, there is no arrows in the field. But if I'm removing the ranging rods P and Q, I will keep that wooden pegs there because I need the positions of P and Q in my field. Yeah, they are used to represent relatively permanent points which have to be retained until the end of the survey. Relatively permanent points. To represent them, we use this particular wooden pegs. That's it. Example would be like the end stations of a survey line, terminal stations of a survey line, or also the center of an instrument, etc. Yes. Okay. And these are the standard dimensions of our wooden peg, 15 centimeter station of a survey. Will be there for the peg, and 2.5 by 3.5 or 3 centimeter by 3 centimeters is also there. Such informations are absolutely useless for gate examination, right? Absolutely useless for gate examination. Even for engineering services, don't study the dimensions of the instruments. Not at all important for us. But in some PSC examination, they will ask. For example, in Karnataka PSC and all, they have asked the dimensions of certain instruments. Yes. So for PSC only, for State Service Commission examinations, you can go through this. For gate and all, for ESC and all, absolutely wasted. Don't study these dimensions. Okay. Next step. Right. Our next instrument is nothing but our ranging rod. Yeah. So how does a ranging rod looks like? This is how the ranging rod is looking like. Now, what is the purpose of a ranging rod? Let me explain this very briefly. Ranging rods are used for the purpose of ranging. Obviously, ranging rods are used for the purpose of ranging. Now, the question is, sir, what is ranging? See, ranging is nothing but the process of finding an intermediate point. The process of finding an intermediate point. That is what we call it as ranging. Let us use the same example we had before. So imagine this is my survey line. Okay, so you imagine that this is my ground here. This one ranging rod here. I call this point as P. There is another ranging rod here. I can call this point as Q. Okay. So what is the length of the survey line we discussed? We discussed that the length of the survey line is say 120 meters, and I am measuring it by using a 30 meter tape. I am measuring it by using a 30 meter tape. Okay. Yes. Now you see, right? What will happen? How many people are there? Leader and follower are there. So leader is there, follower is there. So the leader will walk towards the point Q. What the follower will do? Follower will hold one end of the handle at the point P. So follower will hold one end of the handle at the point P like this. The leader will go like this. Now, right, we need to know where I should keep the arrow now. Yes, the arrow should be exactly in between P and Q. So to make sure that we get a point exactly in between P and Q, the leader will be carrying a ranging rod like this. The leader here will be carrying a ranging rod like this. So the follower should look at the ranging rod P, should look at the ranging rod Q, and then guide the leader. We will ask the leader to move left and right like this. So I am the follower. I can see the ranging rod P. I can see the ranging rod Q. In between, there is the leader. I will ask the leader to move left and right like this. Whenever he is in between P and the other point Q, I'll ask him to represent that point. Fix the ranging rod. So now I get the intermediate point. This process is known as ranging. Now he will extend the chain up to that point and he will drive the arrow there. Yes. So this process is known as our ranging, and the rod I use for that is what we call it as the ranging rod. From this discussion, you should understand, out of the leader and follower, who should be the more experienced person? Can you please answer? From whatever I just told you, out of this leader and follower, who should be the more experienced person? Should it be the leader or should it be the follower? Please understand, the follower should be the more experienced person, because the follower is guiding the leader to move left and right to get that intermediate point. So the important job of ranging is done by the follower. So the follower should be the more experienced person in this work compared to the leader. So don't think that the leader is leading, he will be the best person. Nothing like that. Right? So the follower has to be the more experienced person. Okay? Yes. So that's the purpose of ranging rod. They are used to represent, or they are used to find intermediate points along the survey. Right? The ranging rods comes in different length. Right? Generally, their length will vary from around 2 to 3 meters. So they are 2 to 3 meters long. Right? They have a diameter of 3 centimeter. 3 centimeter diameter will be there. Mostly they are made up of metal. Wood is also there, but not really used. And it is given alternate bands of red, white, or white, black, etc. So these alternative colors are provided so that we can identify the ranging rod from the background very easily. The width of each of this particular color bands is around 200 mm or 20 centimeter. This was a previous year Karnataka PSC question. Right? What's the width of the color band for a ranging rod? What's the answer? It is 200 mm or 20 centimeters. That was a Karnataka PSC question. Okay. So only for this PSC examinations you remember, not for any other examinations. Not for any other examinations. Okay. Right. So let us write down ranging rods. They are used for the purpose of ranging. They may be made up of wood or mostly tubular steel sections about 30 mm diameter, 3 centimeter, 2 to 3 meters long. Right? They contain bands of alternate bands of white or red black about 200 or 20 centimeters long. That's it. That is our ranging rod. Next. Right. They contain bands of alternate bands of white or red black about 200 or 20 centimeters long. That's it. That is our ranging rod. Next instrument is what we call it as an offset rod or butt rod. See, the offset rod or butt rod looks like this. It looks almost like our ranging rod, but it has two additional features. It looks almost like the ranging rod, but two additional features are there. A hook is provided and an opening is provided. You see, this shaded portion is a slit. That shaded portion is a slit. Slit bole to opening. Yes. Why this hook is provided? Hook is provided to hook that glue, or hook is provided to hook my chain and pull it through difficult terrain. See, sometimes what happens is, when we are doing our chain surveying in the field, our chain has to be taken through some difficult bushes. Right? We may have to take our chain through some difficult bushes like this. So imagine this is a ground we are having, and there is a bush here. Jhad bolte na Hindi mein, right? There is some difficult bushes here like this. So whenever you see a difficult bush like this, will you go and put your hand inside to pull the chain? No. Nobody in the correct sense of mind will go and put a hand inside a bush like this. So what we do is, that groove end of the chain is this instrument is there, na? We will insert like this. So here we are having the groove end like this. So this groove end is inserted through the bush like this, and this groove will be used to hook my chain handle. So my chain handle is hooked here. Now what will I do is I will pull it out like this. I'll pull it out. So I can pull my chain like this. I can pull my chain through difficult guitar. Right? That's it. Now what is that slit provided at eye level? Why do we provide an openings at eye level? That is used for setting out. That is used for setting out. So basically, please look at the video. Right, so basically, we are having two openings like this. One opening here and the other opening in this direction. In this direction one opening, this direction one opening. So once this particular openings are in the direction of my survey line, this opening, alright, that means from here I can see the ranging rod P. From here I can see the ranging rod Q. So once this is aligned, if I look through the slit, I can get a 90-degree offset. Okay, I can get a 90-degree offset. So that particular slit is used to set out 90-degree offset. To set out 90-degree offsets. That's it. Okay. Right. So you read that statement here. So they look similar to ranging rod, except for hook provided at the top and a slit provided at the end. The hook is used to hook and pull the chain through difficult terrain, and the slits are used to align offset. And this instrument is also used to measure short offsets. Please remember. Okay. The length of this particular instrument is fixed, so it can also be used to measure short offsets. Please remember. It can also be used to measure short offsets. Yes. Right. Next. Next instrument that we need to talk about is crossstaff. So crossstaff is the actual instrument that we use to do the setting out work. Okay, please remember, crossstaff is the actual instrument that we use in our field to do the setting out work. Is the actual instrument that we use to do setting out work. Okay, so the crossstaff is an instrument that is used to set out offsets here. Actually, not the but rod and all. Okay, what are the different types of crossstaffs that we have? What are the different types of crossstaffs? First one is what we call it as an open crossstaff. Okay. So what do you mean by open crossstaff? Right. What do you mean by an open crossstaff? An open crossstaff looks like this. So it basically consists of a wooden block, okay, in which there are two slits. The white lines represent slit. The slits are at 90 degree. The slits are kept at an angle of 90 degree like this. Okay. So whenever we set out offsets using this particular instrument, I can only get 90 degree offset. I can only get 90 degree offsets to the open crossstaff. Yes or no? Yes. The second type of instrument that we have is what we call it as a French crossstaff. Second instrument we have is a French crossstaff. Using a French crossstaff or not? Yes. The second type of instrument that we have is what we call it as a French crossstaff. Second instrument we have is a French crossstaff. Using a French crossstaff, we can set out both 90 degree and 45 degree offset. We can set out both what? 90 degree and 45 degree offset, because it is having an 8-sided body, an octagonal shaped body is there. And finally, the third one what we have is an adjustable crossstaff. So adjustable crossstaff will give us any angles. Okay. So these are the three instruments that we use to set out offsets. These are the three instruments that I use to set out options. Okay, wrench crossstaff, adjustable crossstaff, as well as our open crossstaff. Yes, right. Next, we have another instrument known as plasterer's lath and vise. Right. See, it's a very less commonly used instrument, but for the sake of discussion, we should know. See, plasterer's lath is a plasterer's lath is a straight rod that I use for the leveling work. Sorry, not leveling work, for the finishing work. Plasterer's lath is a straight rod that I use for my finishing work. Right. So, for example, if you look at your home, you can see that once the masonry work is completed, we will finish the walls by using some sand cement mortar. Right, we will throw it onto that masonry work and we'll finish it using a straight rod. That rod is what we call it as the plasterer's lath. So whenever our survey pass through any construction works, what we'll do is we'll take this lath and we'll insert it vertically onto the ground. So this is the lath which is exerted vertically on the ground like this. Right. Now what we do is, right, we will make a vertical cut here, and inside that cutter we will insert a white cardboard. So this is our white cardboard. Okay, and this cardboard will be having a dimension of around 45 centimeter by 45 centimeter. Okay, now this is used to represent intermediate points along a survey line. So you see, they are used to represent intermediate points along a survey line. What would be an example for this, sir? Can you give an example for this? Let us see whether it is possible or not. So we will go back to our terminologies here. Yeah, we'll go to this terminologies here. So tell me, what is the point P here? P is right. What is this point P? Subsidiary survey station. How do I represent the point P on the survey line AB? On that line AB, how do I represent the point P? I can represent it by using the plasterer's lath and vise. I cannot use an arrow because arrows are only for the end of my survey line. I can use wooden pegs. No. And what will I use? I can use my plasterer's lath and vise to represent the subsidiary survey stations. So that would be a very good example of where I can use your plasterer's lath and vise. Yes. So now let us go back to our last instrument to discuss. So what is the last instrument that we will discuss here? It is nothing but the plumb bob. Right. So have you seen a plumb bob? Yes, definitely. This is how a plumb bob will look like. Right. So what is the purpose of this plumb bob? What is the purpose of this plumb bob? Let me ask you, other than surveying, where have you seen this particular plumb bob? You can see this plumb bob with our masons. Yes or no? With the construction masons are there. Yes. So once the formwork for our let us say column is finished. Once the formwork, that wooden shuttering we call it, is finished for a particular vertical column, right? What we will do is the head mason will come to this particular shuttering work, and from the side of his lungi, he will take this particular plumb bob out, right? But then what he'll do is he'll fix this square block. The square block, you see, square block to this formwork, and he will feed the thread. So this bob will come down. Now how the bob and the square block should be? They should be tangential. So whenever the square block and the bob are tangential, I can understand that our formwork is vertical. So basically, what the mason is trying to do is to check whether the formwork is vertical or not. So I can say like this: the plumb bob is used to check verticality of the the shuttering work. Yes. Also in surveying we use for shuttering work. So I can write like this: they are used to check verticality of ranging rods and also for centering work. These are the two purposes of our plumb bob: to check verticality of ranging rods and also for doing centering work. That's it. Okay. So this is the last instrument I use in our chain surveying. That's it. Now let us see, how does a chain survey proceed? How do I proceed a chain surveying work? See, chain surveying work will be proceeded by basically doing two operations. What are they? Number one, what we call it as ranging. Right? After ranging, we do the second process known as chain. Okay. So always remember this. The chain surveying work will proceed by doing two operations. They are ranging and chain. First job is to do ranging. Right? At the end of ranging, what we will get? At the end of ranging, we will get intermediate points. Yes or no? Yes. What is the job after that? Measure the horizontal distance between the intermediate points. That is your chaining work. Yes. So let us start with our ranging. So I have already I've already explained how this particular ranging is done. Two people are there, leader and follower is there. Follower will hold one end of the chain, leader will take the other end and walk towards the survey line. Out of this leader and follower, who will do the actual ranging work? The follower will do. So the follower will guide and we will ask the leader to move left and right until he is exactly in between the end stations of P and Q. That process is what we call it as ranging. Yes. But before we further proceed, let me ask you, what is the condition for doing ranging? Do we have to do ranging every time? Do we have to do ranging all the time? The answer is not really. Yes. So let us try and understand that. So imagine this is our ground here. This is our ground here. What is this? This is my point P. This is my point Q. Okay. What is the length of the survey line? Let me say the length of the survey line is 120 meters. And to measure the survey line, I am giving you 30 meters. To measure the survey line, I am giving you 120 meters. So the survey line is 120 meter long. I am giving you a 30 meter chain to measure it. Please tell me, do I need to do ranging here? Yes or no? Do I need to do ranging here? Yes, definitely I need to do ranging. Right, because I cannot measure the entire 120 meter at once. But now look at this. I'll change the length of the survey line to 12 meters. So if the survey line is only 12 meters, and if your chain line is 30 meters, can you measure the entire 12 meter at once? Absolutely yes. You can measure the entire survey line at once. So the condition for ranging is that, the survey line should be greater than the given chain. So when the survey line is greater than the given chain line, that is when we go for ranging. So you see this, ranging is nothing but the process of finding intermediate points in between the terminal stations of the survey line. Process of finding an intermediate point where in between the terminal stations, end stations of the survey line. Okay? And ranging need not be done if the survey line is shorter than the given chain. Ranging need not be done if the survey line is shorter than the given chain. Please remember that. So that is the condition for ranging. Now what we'll do is we'll discuss about the different types of ranging. What are? Please remember. So please remember, we are going to see three different methods or three different types of ranging. Now, how a question will be framed for this? Yes, you can get a question. How a question will be framed? See, nobody will ask you how you do a method of ranging. For example, the first ranging is direct ranging. Nobody in your examination is going to ask you how direct ranging is done. What they will ask you is when direct ranging is done. So don't worry about how it is done in the field. Worry about when it is done in the field. What is the field condition for doing direct ranging? So always worry about the when part. Don't worry about, sir, how will I do it? That you don't worry. You just worry about when. What is the field condition? Okay, because questions will be framed like this. If you are having conditions like this and this, whichever the following method of ranging is adopted, or direct ranging is adopted for which of the following conditions, A, B, C, D. So like this, our questions will be framed. So you be careful. Yes. So let us start with our first ranging. That is nothing but direct ranging. Please remember, direct ranging is possible only if the end stations of the survey line are intervisible. When will I go for direct ranging? Only when the end stations of the survey line are intervisible. What do you mean by the term intervisible? Intervisible means we can see the point. Okay, standing at one end, the other end is visible. That is the meaning of intervisibility here. Okay, so for example, if this is my ranging rod P here, this is my ranging rod Q here. Okay, I call this as P, I call this as Q. When will I go for direct ranging? I'll go for direct ranging only if when I stand here at the point P like this, I can see the points P and Q. If both points P and Q are intervisible for me, that is when I'll go for this method of ranging. Okay. So basically, I was explaining this example so far. Whatever discussion we had was about this particular example. Okay. Right. Now, this particular direct ranging can be done in two ways. This direct ranging can be done in two ways. First is by eye adjustment. So basically, what I told you is eye adjustment. So the follower will stand here. He will look at the leader. He will guide the leader to go left and right until he is exactly in between P and Q. Okay, that is what we call it as direct ranging by eye adjustment. That is what we call it as direct ranging by eye adjustment. But the problem is that this can lead to confusion because as per my perspective, I will see that this is the intermediate point. But for somebody else, this might be the intermediate point, and for the third person, this might be the intermediate point. So from people to people, the perspective of the eye will change. So that can lead to certain degree of confusion. So to avoid this from happening, we use a minor instrument that is known as a line ranger. we use a minor instrument that is known as a line ranger. So line ranger is an optical device. Now using this optical device, we can eliminate the confusion of eye perspective, because the line ranger will only give you one unique solution. It cannot give you multiple solutions. It can only give you one unique solution or one unique intermediate point in between the end solutions. Understand? Yes. So questions in your examinations will be framed like this. A line ranger is used for the following ABCD. What is the correct answer? A line ranger is used for direct ranging. Or they will make it even more interesting by saying a line ranger is adopted only when the field condition is dash. What is the field condition? The field condition is points should be interruptible. Understand? So like this, questions will be framed. So I'll repeat this again. Don't worry about the how part. Worry about the when part. When, what kind of field condition, what kind of work can be done. Okay? Yes. Right. So let us go to the next condition. What if the end stations of the survey line are not intervisible? Then direct ranging is ruled out. We'll go for the next method. That is reciprocal or indirect ranging. Okay. One second. Right, reciprocal or indirect ranging. Okay, so whenever the end stations of the survey line are not intervisible for us, we'll go for this reciprocal or we go for this indirect ranging. Okay, that's it. Why the end stations are not intervisible? Why do you think the endpoints are not intervisible? You see, the endpoints are not intervisible because our ground condition is looking something like this. Okay, the endpoints are not intervisible because let us assume the ground condition looks something of this fashion. The ground condition looks like this. Okay, right. You can imagine that. Right, we are having the ranging rod P here like this, and we are having another ranging rod say Q here like this. Okay. So this is the once. Okay. So that is the ranging rod P. That is the ranging. At all you want to do reciprocal ranging, there is one more condition that needs to be satisfied. What is the second condition? Terminal stations are not intervisible. Okay, first condition. What is the second condition? The second condition is that somewhere along the survey line PQ, you should have some intermediate points from which both P and Q are intervisible. Somewhere along the survey line PQ, there should be some intermediate points from which both P and Q are intervisible. Then only reciprocal or indirect ranging is adopted. For example, imagine this point here. Say R. So imagine I am standing at the point R. Standing at the point R, can I see the points P and Q? Yes or no? Please give me an answer. When I am standing at the point R, can I see the points P and Q? Right? Everybody says no. I know. The answer is yes. Okay. To solve your confusion, you imagine this is me standing at the point R. So I am standing at the point R like this. So standing at the point R, can I see the point P? Absolutely yes. Similarly, can I see the point in Q? Yes or no? Now tell me, is it yes or no? Now tell me, is it yes or no? Not Q. Yes, Tushar. But what about now, Tushar? Now it is yes. Now why do you say yes? Now why do you say yes? Because you see, when I was showing you a hill like this, when I was saying the ground looks like a hill, you are thinking about Mount Everest. That is the reason. You said no first. When I am saying that the ground condition looks like a hill, you are thinking about Mount Everest. That is the reason first you said no. Please understand, we don't do chain surveying in Mount Everest. Nobody will do chain surveying in Mount Everest. No chaining is done in mountainous region. So this is not a mountain actually. This is just a small elevated portion of the ground. Remember the field condition for chain surveying. It is adopted when the ground is fairly level. It is adopted when the ground is fairly level. Yes or no? Yes. But do you think that 100% of the time you will get an exactly horizontal ground? No. Right? Some sort of elevated ground will be there. Yes. So this is a small elevated ground. We can just climb on top of it. We can just walk and just climb on top of it. Just a casual, uphill will be there. You just climb it and so that is the condition we are talking. We are not talking about any Mount Everest or anything. Okay, that's it. Okay, so let us recollect the condition once again. So when will I go for reciprocal ranging? I go for reciprocal ranging when the terminal stations are not indivisible, but there exist some points from which both P and Q are indivisible. Right. So one such point is R, another such point is S. I can imagine me standing at the point S like this. Now I can see the points P and Q from S. I can see the points P and Q from the point S here. Now the question is, how do I establish the points P and Q? How do I establish the point P and Q? Let me slightly explain. Right. So imagine this is the real condition. So tell me, what is this view? What is this view? This is nothing but the elevation view. So no, right, of the survey line view. This is the elevation view. Can you please tell me in the plan view? In the plan view, how does the survey line look like? The survey line PQ will look like a straight line. In our plan view, the survey line PQ is going to look like a straight line, no doubt. Yes, this is P and this is Q. See, initially, I cannot come and stand directly upon the point R and S. I don't know where the point R and S is, so I cannot come and stand directly on the point P and R and S. So what I'll do is I'll stand slightly away from the survey line at this point here, say R1. I'll stand slightly away from the survey line at a point R1. Similarly, my friend will be slightly standing away from the survey line at this point here, say S1. At this point here, what is that? That point is S1. So my first friend is R1, my second friend is S1. Let us call R1 as say Ramesh and S1 is say Suresh. So my two friends are Ramesh and Suresh. Ramesh is standing at R1, Suresh is standing at S1. Okay. Now please understand, standing at R1, Ramesh can see P and Q. Standing at R1, Ramesh can see P and Q. Similarly, standing at S1, Suresh can see P and Q. Standing at S1, Suresh can see P and Q. So now, yes, right. Now what Ramesh will do is, standing at R1, Ramesh will look at the point Q. Ramesh will look at the point Q. Now, what he will do is, he will ask Suresh, Suresh to walk towards the survey line. He will ask Suresh to walk towards the survey line. Okay, so you see, this is where Suresh is standing initially. Right, so this is where Suresh is standing here, S1. So Ramesh is now looking at point Q. He will ask Suresh to walk towards the survey line. So Suresh will walk towards the survey line until he reaches this point here, S2. Do you know what happens at S2? At S2, Ramesh, Suresh and Q are the same straight line. At S2, Ramesh, Suresh and Q are the same straight line. Now, standing at S2, what Ramesh will do? Standing at S2, Ramesh will now look at the point P like this. Ramesh will now look at the point P like this. And now, he will ask, Suresh will now look at the point P like this. Standing at S2, Suresh will look at the point P like this. And now, he will ask Ramesh to walk towards the survey line. He will ask Ramesh to walk towards the survey line until Ramesh reaches this point. What is that point? That is R2. Reaches this point, that is R. Now the process is repeated. Ramesh standing at R2 will again look at the point Q like this. He will ask Suresh to walk towards the survey line until Suresh reaches this point here. Who is that point here? That is S3. So Ramesh, Suresh and Q are the same straight line. So slowly, right, what happens? We will reach this point here R on the survey line and slowly I'll reach this point S on the survey line. So you can imagine that this is the ranging rod we have kept at the point R, established at the point R. This is the ranging rod we have established at the point S. Now tell me, right, standing at R, can I say R, S and Q are in the same straight line? Yes. Standing at R, I can say R, S and Q are in the same straight line. Similarly, standing at S, can I say S, R and P in the same straight line? Yes. I can also say S, R and P are in the same straight line. So what is my final conclusion? The final conclusion is these 3 points, P, R, S and Q, the 4 points are in the same straight line. This is how reciprocal leveling is done. Right. Small explanation also I've done regarding the field procedure. Yes. Let us write down the theory behind that. So when will I go for reciprocal or indirect ranging? It is adopted when the terminal stations are not indivisible. It is adopted when the terminal stations are not indivisible. Okay, but apart from that, what's the next condition? Also, it requires some intermediate points from which the terminal point should be indivisible. Standing at P, I cannot see the point Q. Okay, but there are some intermediate points from which the end stations are visible. Then only I can go for this particular method. Example is small hills. I'll write hills only, but please don't think about Mount Everest. Please don't think about Mount Everest. I hope. Particular discussion is here. Right. Now, what if you don't have the second condition satisfied? That means the end stations of the survey line are not intervisible. At the same time, there is no intermediate point from which the end stations are intervisible. Standing at P, I cannot see the point Q. Similarly, there is no point in between P and Q from which both the end stations are visible. Right. So, other as a condition, if you don't have that second condition, reciprocal ranging is ruled out. You have to go for the next method here. What is that known as? It is known as a random line. That is known as random line. Let me explain the field condition here. So, this is my ground here. This is my ranging rod at P. This is my ranging rod at Q. Right. Standing at P, I cannot see the ranging rod Q because there is an obstruction here. There is an obstruction here. Right. And if I come and stand anywhere between the points P and Q like this, I am unable to see the point Q and I am unable to see the point P. What is the example for this field condition? The best example is nothing but a forest. Right. So if you are having a survey line across a forest, standing at one point, can you see the other point? No. If you come and stand inside the forest, will you be able to see the end points? Not necessarily. So, right, this condition requires the third method of ranging. We call it as the random line method. Okay. Right. So, what is this statement? Please read this. It is adopted when the terminal stations are not intervisible and there exists no intermediate points from which terminal points are intervisible. It is adopted when the terminal stations are not intervisible and there exists no intermediate points from which the terminal points are intervisible. That is when I go for this random method. Don't worry about the field procedure of random method. Okay, so that's it. These are the three methods by which we can do our arrangement. Okay, so remember the field conditions for which the particular method is adopted. So for points across a forest, the method of ranging adopted is random line method. For points across a forest, the method of ranging adopted is random line method. Right. For reciprocal leveling is adopted for option A, open grounds. Option B, forested area. Option C, hilly ground. Option D, both the B and C. What is the correct answer? The correct answer is hilly areas. Understand? So like this, upon the field conditions, questions will be framed. Make sure that you are comfortable with the field conditions. Okay, that's it. So these are the discussions regarding our ranging. Tell me, once the ranging is completed, what will you get? At the end of ranging, what will we get? We will get intermediate points. Correct? Huh? At the end of ranging, what we get? We get intermediate points. Yes. What is the next step? The next step is to extend the chain between these intermediate points so that you get what? You get your horizontal distance. The next step is to extend the chain between the intermediate points so that you get a horizontal distance. What is that process known as? That process is known as chaining. Okay, so that's our next discussion. What is meant by chain? Now, before I start this discussion, let me say one point very clearly. Whenever I extend the chain between 2 points, what do I want? I want the horizontal distance. See, it is not necessary that the ground is horizontal. There is no guarantee that the ground is horizontal. The ground may be sloping up. The ground may be curved. The ground may be undulated. I don't care. Okay, I don't care. Right. I always want the horizontal distance. Even if the ground is inclined, even if the ground is curved, even if the ground is undulated, whenever I put the chain between 2 points, I only want the horizontal distance between them. I don't want any other distance bigger. Understand? So please remember, this is the first understanding. Whenever the ground is horizontal, no problem. But the problem starts when the ground is sloping. So we'll be concentrating mostly on chaining on the sloping ground. We'll be concentrating mostly on chaining on sloping ground. So please remember, chaining is the process of extending the chains between 2 points to obtain horizontal distance. Extending the chain between 2 points to obtain horizontal distance. Horizontal distance. I don't want any curved line. I don't want any inclined line. I don't want any undulated line. I only want the straight line horizontal distance. Okay. Yes. Now let us look at the methods of chaining. Right. Now the first. Right. I only want the straight line horizontal distance. Okay, yes. Now, let us look at the methods of chaining. Right. Now, the first method, the most important method is known as Method of stepping are also known as direct method. Method of stepping are also known as direct method. So how is my ground? Obviously my ground is undulated. My ground is sloping lines. Okay. This is how my ground is looking like. This is how my ground is looking like. Okay. Right. You can imagine this is my point P. You can imagine this is my point Q. So these are the 2 points P and Q that we are having. What are we supposed to measure? We are supposed to measure the horizontal distance between them. We are supposed to measure the horizontal distance between them. So tell me how many people are involved in this surveying worker, chaining worker? 2 people are there who are there, leader and follower. So both the leader and follower will come to the point P. My leader and my follower, both of the point will come at the point P. What will happen is the follower, he will hold one end of the chain on the point P. Follower will hold a 0 meter end of the chain on the ground like this. What the leader will do is he will walk down the slope. You see, the leader will walk down the slope. He will take the other end of the chain and he will walk down the slope. After walking certain distance, he will stop, and what he'll do is he'll make the chain horizontal. After walking a certain distance, what he'll do is he will stop and he will take the chain and make the chain horizontal like this. He will measure this length as L1, and using a plumb bob, what he will do is he will transfer this particular point onto the ground. Right, he'll measure the length as L1, and using a plumb bob, he will transfer that particular point onto the ground. He'll transfer the point onto the ground like this. Okay, right. Now what happens is once again. Right, so he has transferred the point onto the ground. Now what happened is, right, the follower will follow him, and the follower will reach here. So now again, both the leader and follower is at this point. What the leader will do? The leader will again, so this is the leader walking on, okay? So again the leader will walk down the slope like this, right? And after reaching a certain point, again he'll take the chain and he'll make the chain horizontal like this. Measure this length as L2, and what he'll do, he will transfer the point onto the ground like this. Okay, right. Now I hope you get the idea. The procedure is repeated. So he'll again walk down the slope until the other end point is reached. He'll make the chain horizontal, measure this length as L3, and make sure that the centering is done exactly above the point Q like this. Okay, right. Now, if anybody asks you, what is the horizontal distance D here? What's the answer? Horizontal distance D is nothing but L1 plus L2 plus L3, or simply summation of all the L values. Summation of all the L values. This is our horizontal distance D. It is going to be the summation of all the L values. Yes. So this is how the method of stepping is done. Because you can see that some step-like structures are formed here. So no, some step-like structures are formed. Yes. Now, you might be thinking, sir, how do I make sure that that particular chain is horizontal? How will I make sure that chain is horizontal? So to make sure that the chain is horizontal, we can use an instrument known as a clinometer. We can use an instrument known as a clinometer. So the clinometer is used to measure slope angles. This clinometer is used to measure slope angle. So it will be having a needle represented by the arrow here. That arrow there, that is the needle. So the reading here will be 0 degree. The reading here will be 90 degree. And here also, the reading will be what? 90 degree. The reading will be 90 degree. Yes. So to make sure that the chain is horizontal, I'll take this clinometer and I'll hold it here like this. I'll take the clinometer and I'll hold it here like this, such that the reading becomes equal to 0. So whenever the reading is 0, the slope angle is 0. Slope angle 0 means what? The chain is horizontal. This is how I'll make sure that the chain is horizontal. Okay now? Yes. Now, how did I transfer the point? Once I made the length horizontal at L1, how did I transfer the point? By using a plumb bob. Another instrument you can use to transfer the point onto the ground is an arrow like this, which is attached with an extra weight. So I can use an arrow like this, and in this arrow, some additional weights will be there. In this arrow, you can see that some additional weight is also attached. What do you call this arrow as? You call this arrow as a drop arrow. You can call this arrow as a drop arrow. So this was asked in Tamil Nadu PSC. In Tamil Nadu PSC, once they asked there, like, what is or where do you use the drop arrow? Drop arrow is associated with which method of chaining? The answer is method of stepping or direct method. Yes. So these are some small information. But in your GATE examination, one very important question they will ask you is this: how is this method conducted? How is this particular method conducted? Please remember, this method is conducted downhill. Please remember this. The method of stepping is best conducted downhill. So this is a question that they will regularly ask. Okay, we don't go uphill. It's difficult for us to hold the chain horizontal. So leverage will not be that. So what we do is we will conduct this method downhill. That's it. So this is the method of stepping. So you see this. The follower hold one end of the chain in the ground. The leader walks down the slope, makes a certain distance horizontal, transfers the point onto the ground. Okay, right. Next, the process is repeated up to the next terminal station. Like the most important point is the best suited when the conducted down. Method is best suited when conducted down. That's it. So this is the first method of chaining, which is known as the direct method or method of stepping. That's it. will stop here for today. Okay, the last 5 minutes we will take for calculations. So this is the description. Good morning. Good morning. Shading. That was the direct method. Okay, which is also known as the method of stepping. Okay. So next I will talk about the indirect methods of distance measurement. Okay, let us look at them one by one. So in the direct method of linear measurement or in the direct method of chaining, what happened? What happened is the distance was calculated as sigma L. Distance was calculated as sigma L. That is nothing but L1 plus L2 plus etc. 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 Right? You don't have to apply any formulas there. But when it comes to indirect methods, right, as the name suggests, you will not get the distances directly. You will have to use formulas to calculate the distances. Let us see how that particular method works. Right? Let us see how that particular method works. Okay. So you imagine, our first method is by measuring slopes. Okay. So the first method is by measuring slopes. So imagine that you are having a ground that looks like this. Sorry. Okay, so you can imagine that you are having a ground that looks like this, right? Something in this particular fashion. This is my point P, and this is my point Q. Okay. What are we trying to get? We are trying to get the horizontal distance here, PQ. This is the horizontal distance PQ we are trying to get. Okay. Yes. So what we'll do is, right, bring our chain to this particular point and measure the sloping distance. And we will measure this much sloping distance as L1. Using the instrument that we discussed yesterday, that is the clinometer. Yesterday we discussed that, the clinometer. Right, what I'll do is, I'll measure the slope angle. I'll measure the slope angle here. With respect to the horizontal here, whatever is the slope angle coming, I'll measure here is theta 1. If I know the slope angle and if I know the sloping line, what is the horizontal distance? It will be L1 cos theta 1. The same procedure is repeated with respect to the horizontal here. Measure this much sloping length as L2. Measure the slope angle as theta 2. What is the horizontal distance again? L2 cos theta. Okay. So that is how distances will be measured. Finally, at the end of the day, what is the horizontal distance be? It will be equal to summation of all L cos theta values. It will be the summation of all L cos theta values. That is my horizontal distance D. The horizontal distance D is summation of all L cos theta values. That's it. So here we need to use the instrument known as clinometer. That is the first indirect method. The second indirect method is by something known as by measuring elevations. Right. So let us see how this particular method works. You can imagine your ground is going something in this particular fashion. Okay. Again, the ground is something in this particular fashion. Like this. Okay. So this is my point P here. Yeah. This is my ground. Okay. And this is my point Q here. So in this method, what we do is, we will measure the entire sloping distance at once. You can drive a wooden pin here. You can drive another wooden pin here. What you do is, you measure the entire sloping length as L. Measure the entire sloping length as L. Now, using an instrument known as Abney level, right? Using an instrument known as Abney level. I told you what is Abney level is. But we did one problem in the first chapter about the extended Vernier and all. At that time, I told you levels are usually, level means instrument used to calculate difference in elevation. Abney level is a small instrument that will be used to calculate difference in elevations. But remember, Abney level is basically measuring angles only, vertical angles only. Right? So it is a modified version of our clinometer. It is measuring the angles only, but ultimately we will be reporting the vertical distance using this instrument. Yes. So I got the sloping length. Using the Abney level, what I can do is I can calculate the difference in elevation. The particular difference in elevation is taken as h. So just use our Pythagoras theorem and tell me what is the horizontal distance D. What is the horizontal distance D? D will be nothing but equal to under root of, right, hypotenuse square minus h square. So that is the horizontal distance D. If you want, you can measure it in small part, right? So we'll get under root of L1 square minus h1 square plus under root of L2 square minus h2 square. We can do like that. Or else at a stretch also, if it's possible, we can do that. Okay, yes. So this is by measuring the elevation using the instrument known as Abney level. Yes. See, there is nothing much to it. Just for the sake of discussion, we need to go through it. Now, the third method is different and this is slightly interesting. Okay. The third method or the third indirect method of horizontal distance measurement is by something known as hypotenusal allowance. Now, what do you mean by this hypotenusal allowance? The definition is like this. It is the correction applied per chain length. What is hypotenuse allowance? The correction applied per chain length along a slope. So that what happens? Horizontal distance covered will be equal to say one chain length. Correction applied after every chain along the slope so that horizontal distance becomes equal to one chain length. That is the definition of hypotenuse allowance. Let us try and understand what that means. So you imagine you are having a sloping ground like this. You imagine that you are having a sloping ground like this. Okay, right. So this is my sloping ground. I call this particular point as A, right? This is our sloping ground like this. Let me say that with respect to the horizontal, okay, it is making an angle of theta. So we are having a sloping ground making an angle of theta with the horizontal. Okay. Now what I'll do is along the slope, listen carefully, okay? Along this slope, right, I'll put my one entire chain length. If it is a 20-meter chain length, along this particular slope, that one entire 20-meter chain length I'll put like this. Use your logic and please tell me, if so, what is the corresponding horizontal distance I can travel? If I put one entire chain along a ground at an angle of theta, okay, what is the corresponding horizontal distance I can travel? What is this distance I can travel? It will be nothing but we just discussed that. One chain length times cos theta. So along the slope, when you put one entire chain, the corresponding distance you can travel horizontally is one chain length times cos theta. But is this one chain length cos theta greater than one chain length or less than one chain length? Please answer me. Yes, very good Tanvi, very good Aditya. Yes, Chandra. Your answers are absolutely correct. This particular distance, one chain length cos theta, will be 100% less than one chain length. Yes or no? Yes. So I don't want this horizontal distance. Okay. What I want is, I want the horizontal distance covered to be equal to one chain length. So if I want the horizontal distance covered to be equal to one chain length, what should happen to the sloping distance? Let me call this point as B. Okay, let me call this as B. So initially my sloping distance was AB. Now if I want the horizontal distance covered to be equal to one chain length, what should happen to the sloping distance? The sloping distance should increase from AB to AB dash. Can you see that? Right, the sloping distance should be increased from where to where? From AB to AB dash. So this extra amount by which you are increasing the sloping distance, is what we call it as hypotenuse allowance. Okay, right. So this is the concept behind our hypotenuse allowance. The amount by which the sloping distance is increased. Initially the sloping distance is AB, but I am increasing it by BB dash. So that amount by which the sloping distance is increased so that the horizontal distance covered AC is equal to one chain length. That extra sloping distance is what we call it as hypotenuse allowance. That's it. I will quickly repeat this once again. So you are having a ground sloping like this. In the sloping ground, if I put one entire chain, the horizontal distance I cover is less than this one chain length. So if I want the horizontal distance covered to be equal to one chain length, what should happen to the sloping distance? The sloping distance should be increased by an amount of HA. The extra amount by which you increase is what we call it as hypotenuse allowance HA. I hope you understood that. Okay, yes. So what is the value of this hypotenuse allowance? How can I calculate hypotenuse allowance? Hypotenuse allowance HA is nothing but BB dash, which is nothing but AB dash minus AB. Yes. Now, in this triangle, if I take cos theta, what is cos theta? Cos theta will be nothing but adjacent side AC by hypotenuse, that is nothing but AB dash. Now, remember, AC value is equal to one chain, okay, and AB dash is the hypotenuse. From this, what is AB dash? AB dash will be equal to one chain length by cos theta, which is one chain length into secant theta. Now, remember, our AB distance is also equal to one chain length. From the figure, you can see that distance AB is equal to one chain length. So if you substitute all of them together, what is the hypotenuse allowance? AB dash. AB dash is one chain length into secant theta, minus AB is again one chain length. So if I take one chain length common outside, this is my formula. Hypotenuse allowance is equal to one chain length into secant theta minus 1. Hypotenuse allowance is equal to nothing but one chain length into what? Secant theta minus 1. Okay, right. So this is the formula for our hypotenuse allowance, right? So remember, if you look at this formula here, hypotenuse allowance depends on two factors. Number one, chain, length of the chain, okay? Number two, theta angle, that is the slope angle. From this formula, hypotenuse allowance depends on chain length and depends on the angle theta, slope angle theta. But if you really think about this, the chain length remains constant, correct? If I am giving you a 20-meter chain for a survey, all throughout the survey, the chain length will remain 20. So 2 remains constant here, chain length remains constant. So then I can say hypotenuse allowance depends only on what? Hypotenuse allowance depends only on the slope angle theta. Okay, right. So what you do is, for every slope angle, whenever the slope angle theta changes, you calculate your hypotenuse allowance and you increase the sloping distance by that amount. Okay, right. So let us take a small example here. So just imagine that the value of theta is something like 30 degrees. You just imagine that you got theta as something like 1 degree. You just got theta value as something like 1 degree, 30 degree, and your chain length is say 20 meters. Your chain length is 20 meters, and you substituted everything in our equation. You got hypotenuse allowance as say 1 meter. You got hypotenuse allowance as how much? 1 meter. You got your hypotenuse allowance as 1 meter. So tell me, what is the meaning? So the meaning is that, right, if this is your sloping ground, right, you need to put your 20-meter chain length like this. You need to put your 20-meter chain length like this. Now what you do is, you pull the entire chain forward. What you do is, you need to pull the entire chain forward. This entire chain, you pull forward by how much? By hypotenuse allowance. Okay. So this is where your chain is. Okay. This is where your chain is. What you do now is, you pull this chain forward. Okay. You pull that chain forward by how much? By the hypotenuse allowance, that is the 1 meter. So then what happens? The horizontal distance covered is equal to what? That chain, that is 20 meters. Now, again, from this point, you put your 20-meter chain, right? If theta angle is the same, again you pull forward by 1 meter. What is the total horizontal distance covered? 20 plus 20, that is equal to 40 meters. So, you applied hypotenuse allowance one time, your horizontal distance is 1 chain length. One more time you apply your hypotenuse allowance like this, the total horizontal distance becomes 2 chain length. So, in the field, if I apply hypotenuse allowance, say 5 number of times, what is the total horizontal distance I moved? It will be equal to 5 chain length. It will be equal to what? 5 chain length. So now our calculation becomes very easy. Okay. So just to count how many number of times you applied hypotenuse allowance in your field, multiply that with your chain length, you get your horizontal distance. So it is defined as the amount by which the chain is pulled forward. Okay. Amount by which you pull the chain forward along the slope so that horizontal distance covered is equal to that chain length. Okay. That is the idea. So you see what is meant by hypotenuse allowance? It is the correction applied per chain length whenever the theta slope angle changes, or it is the amount by which the chain is pulled forward along the slope such that horizontal distance covered is equal to that chain length. So if you apply hypotenuse allowance n times, right, then the total horizontal distance will be what? N times that chain length. That's it. Okay, so it is very easy for us in the field to calculate our distances. So that is our hypotenuse allowance. Yes. So we finished the discussion on the method of ranging yesterday, and now we have finished the discussion on method of chaining. Okay. So ranging is the process of finding intermediate points. Okay. Chaining is the process of finding what? The horizontal distance between the point. You can do that by 3 methods. In fact 4 methods. First one is direct method, the method of stepping. Okay. Second is by measuring the slope angle. Third one is by measuring the elevation, and fourth one is by measuring the hypotenuse. Okay, whichever is most suitable for your field, you can measure it. Okay, right. Now we'll move on to the most important discussion in this chapter. The most important discussion in this chapter, that is nothing but the error due to incorrect chain. Okay, without knowing this numerical here, this is a numerical. Okay, without understanding this numerical, you'll not be able to solve any of the following questions. Right? You'll not be able to understand the concept behind the problems. Okay, so be very careful. Listen to this discussion very closely. Okay, yes. First and foremost, what do you mean by an incorrect chain? Can you tell me? First and foremost, what do you mean by an incorrect chain? What do you mean by an incorrect chain? Anybody? What is the meaning of a chain is incorrect? For example, when will I say a 20-meter chain is incorrect? When will I say a 20-meter chain is incorrect? Yes, very good. Right? When it is not equal to 20 meters. I'll say that my 20-meter chain is incorrect when it is not equal to 20 meters. So what are the two possibilities? The first possibility is that the chain is greater than 20 meters. So you imagine you are applying your pull for a long duration of time, right? And slowly what happens? The circular rings in the chains will open up. The circular rings in the chain will open up. So as the circular rings in the chains are opening up, what will happen to my horizontal distance? What will happen to my chain length? My chain length will definitely increase. So my 20 meter or my 30 meter chain will be greater than 20 or 30. This condition is known as chain is too long. This condition is known as chain is too long. Similarly, what if somebody steps on the chain linker? If somebody steps on the chain linker, the link will get bent. Initially it is like this, the link is straight. Somebody steps on it, it will get bent like this. It will get bent like this. So as it is getting bent, what is happening to the length of the chain? The length of the chain is getting decreased. Okay, as the chain link bends, the overall length of the chain decreases. So my 20 meter chain or my 30 meter chain will be less than 20 or 30. This condition is known as chain too short. Okay, this condition is what we refer to as the chain is too short. Okay, now please. Let us try and understand the numerical behind the first condition where we will consider the chain is too long. So we'll start with the first condition. What is that? Chain is too long. We'll start with the first condition that the chain is too long. Listen carefully, okay? Imagine I am giving you a line AB. Okay? So you imagine this is a line AB. I am saying that AB is exactly equal to 30 meters. Okay? So I am giving you a line here AB. And what is the length of the line AB? The length of the line AB is exactly equal to 30 meters. The length of the line AB is exactly equal to 30 meters. Imagine I am giving you a 30 meter chain to measure it. 1 second, okay? Okay, so this is my line AB. And what is the length of the line AB? It is exactly equal to 30 meters. Imagine I am giving you a 30 meter chain to measure it. I am giving you a 30 meter chain to measure it. So there is a 30 meter chain used to measure it. So tell me something. If the chain is exactly equal to 30, what should happen? What should happen? Like if I keep the 0 meter end of the chain here, if the chain is also exactly equal to 30, where should the 30 meter end of the chain come? Where should the 30 meter end of the chain should come? It should come exactly at B and say that this is equal to 30 meter. It should come exactly at B and this should be equal to what? 30 meters. Yes or no? Yes. Provided the chain is also 30 meters. But right now, what is my chain or how is my chain? Right now the chain is too long. So if the chain is too long, please tell me where will this 30 meter end will come? Will it come right exactly at B or will it go beyond B or will it come before B? Tell me where will the 30 meter end come? Exactly at B or will it go beyond B or will it come before B? Very good. Everybody given the correct answer. The chain will go, the 30 meter end of the chain will go beyond B. So it will not come and stop here, unfortunately. Right, as the chain is too long, it will continue to go beyond B and say this much is equal to 30 meters. Right? They'll say that this is where the 30 meter of the end is. Right? But remember, I need to measure only up to AB. Correct? I need to take my measurement only up to AB. So if I'm taking a reading at this point on the chain, right? If I'm taking a reading at, you see, this point on the chain, will it give me a value less than 30 or more than 30? Definitely, right? You are going to get a reading that is shorter than 30. You'll get something like, say, 29 meters. Right? So let us understand what is happening. The correct length of the survey line was 30 meters. The correct length of the survey line was 30 meters. But when I measured it with the chain too long, what is the measured length coming? Measured length coming as 29 meters. So tell me, conclude, what is happening? Whenever my chain is too long, what will happen to the measured length of the survey line? Will it increase or will it decrease? The measured length of the survey line will decrease. The measured length of the survey line will decrease. Okay. So this is the inference. Okay, very important. Whenever the chain is too long, the measured length of the survey line will decrease. If so, what is the resulting error? If so, what is the resulting error we will get? The resulting error will be negative error and the resulting correction would be positive correction. The resulting error will be a negative error and the resulting correction would be what? Positive. Okay, now? Yes. I hope you understood that. So what is error? Error is always measured value minus correct value. Measured value is 29, correct value is 30. 29 minus 30 is minus 1. So the measured value decreases the error is negative, correction is positive. So remember, okay. So please look at the video. When the chain is too long, measured length decreases. Too long decreases. Right? If the chain is too long, measured length of the line decreases. Error is negative and correction is positive. Negative error, positive correction. That's it. Okay. So this is the first point that you need to understand. Now let us move on to our next condition where the chain is too short. Okay. So this is our next condition where the chain is too short. Everything remains the same. Okay. Everything remains the same. Let us see what happens. So again, this is my line AB. This is my line AB. What is the length of the line? Exactly equal to 30 meters. Right. To measure this line AB, I am giving you what? 30 meter chain. I am giving you a 30 meter chain. So if the chain is exactly equal to 30 meters, what should happen? If the chain is exactly equal to 30 meters, what should happen? If I keep the 0 meter end of the chain here, where should the 30 meter end of the chain come? The 30 meter of the chain should come exactly at point B. This is the condition where the chain is also equal to 30 meters. But right now, how is my chain? Too short. So where will the 30 meter point come? Will the 30 meter point come before B or will it go beyond B? Please tell me. Will it come before B or will it go beyond B? I think it is very easy, right? As the chain is too short, the 30 meter end will come where? Before B. Yes, very good. So even before I can reach my 30 meter, even before I can reach the point B here, what happens is the chain will get completed here. The chain is now completed here. So we needed to measure again the entire length AB now. We need to measure the entire length AB, so no? Yes. So we need to measure the entire length AB. So up to this particular point B, we need to measure. Right. So already 30 meter chain completed. Together with that, you are measuring something extra. So will you get a value more than 30 or less than 30? Clearly, you get 30 plus something extra. Let me write it as 32 meters. Simply I'm writing. Let me write it as 32 meters. So tell me what is happening. What was the correct length of the survey line? The correct length of the survey line was 30 meters. When I measured it by using my chain too short, what is the measured length I'm getting? The measured length I'm getting is 32 meters. Okay. So you see, the correct length of the line is 30 meters. The measured length of the line is 32 meters. Okay, 32 meters. So tell me what is happening. The measured length of the survey line is going to what? The measured length of the survey line is increasing. So when the chain is too short, what is happening? The measured value of the survey line is increasing. What is the nature of the error? Error is measured value minus correct value. 32 minus 30, you will get it as plus 2. So the error is right positive. So what kind of correction I should give? The correction should be negative. The correction should be negative. Right. So this is the concept. So please remember the second condition. So when the chain is too short, measured length of the line will increase. Okay. When the chain is too short, measured value increase. Short increases. Okay. What is the nature of the error? Positive. The nature of correction is negative. That's it. Okay. So please remember this. Very, very fundamental understanding of chain surveying. Okay. Very important. So please remember. Okay. When the chain is too long, measured length decreases. When the chain is too short, measured length increases. Chain is too long, measured length decreases. Chain is too short, measured length increases. So if the measured length increases, error is positive, correction is negative. Right? If the measured length decreases, error is negative and correction is positive. That's it. So this is the concept of error due to incorrect chain. We need to see the numerical equations here one by one. So let me try and introduce some terms here. What is capital L? Capital L is the designated chain line. Right? Capital L is the designated chain. What do you mean by designated chain line? Whatever written on the chain handle. And what is capital L dash? It is nothing but the actual line. It is nothing but the actual chain line. So L is the designated chain line. What is L dash? L dash is the actual chain line. L dash is the actual chain. So you see here, right? I'm saying that my 30 meter chain. I'm saying that the 30 meter chain is say 10 centimeters too long. I'm saying that 30 meter chain is 10 centimeters too long. So then, what is the value of L? Anybody please tell me. What is the value of L? What is the value of L here? Right, very good. The value of L is nothing but 30. Because when I'm saying that I'm having a 30 meter chain, it is written in the chain handle that it is 30. It is written in the chain handle is 30. No, Tanvi. No. 30 meter, 10 centimeter. Okay, don't make mistake. So, what is capital L? Capital L is designated chain line, which means the value written on the chain handle. So, what is the value written on the chain handle? 30 only. But is the chain actually 30? No. So, what is the L dash value? The chain is 10 centimeter too long. So, it should be 30 plus 10 centimeter means what? 0.1 meter too long. So, what is L dash value? 30.1 meter. Okay. So, the designated value of chain is 30, but the actual value of chain is 30.1. The designated value is 30, but the actual value of the chain is what? 30.1 meters. Understand? Yes. What if it was 10 centimeters too short? If the chain was 10 centimeters too short, what is the L value? What is the designated chain length? It will not change. It will remain 30 only. Because the value written on the chain handle will never change. It will always remain the same. Yes. But what is the actual length of the chain L dash? What is the actual length of the chain L dash? Is it equal to 30? No. It is short now. So 30 minus 0.1. I should get it as 29.9 meters. I should get it as what? 29.9 meters. Yes. Very good. So I hope that you understand your mistake. Be very careful with the unit. Okay. I did not say 10 meter. That is blunder. How can my chain be 10 meter and all too short? That is not correct. Okay. Yes. Now, similarly, what is L dash? L dash is nothing but the measured length of the survey line. L dash is nothing but the measured length of survey line. What are we trying to find out? We are trying to find out the correct length of the survey line. We are trying to find out what? The correct length of the survey line. So tell me, what is the formula for the correct length? The correct length of the survey line is equal to L dash. L is equal to L dash into L dash by L. Okay, right. Measured length of the survey line into L dash by L. That is the correct length. What would be the correct area? Can you imagine? Correct area would be equal to measured area into L dash by L equals square. L dash by L equals square. What is the correct volume? The correct volume will be equal to measured volume into L dash by L the whole cube. L dash by L the whole cube. That's it. This is how the formula works. The correct length L is equal to L dash into right L dash by L. Correct area will be extrapolate. Measured area A dash into L dash by L the whole square. Correct volume is equal to measured volume B dash into L dash by L the whole cube. That's it. So these are the equations. Okay, right. Now directly and indirectly, multiple times we got questions, from the same GATE examination and also in our engineering services examinations. Okay, right. So be careful, right, to understand what is L and what is L dash. Okay. Anyway, this is our formulas. Okay, right. Basically, there are two models of problems that they can ask you from this area. There are two models of problems. Let us look at these numericals. One. Any answers? Very good, Dinesh. Aditya, please check your answer. Yes. Oh, Tushar, no. Chandra, no. No, Bhargav Teja. Right. So most of you have given us the correct answer. Let us see what the solution is. Okay, right. Read the question and identify the parameter. That's it. 20-meter tape was found to be 20 centimeters too short throughout the measurement. The correct length of the line if the measured length was 200 meters. So tell me, what is the value written on the chain handle? What is the value written on the chain handle? Designated chain. What is the value? It is nothing but 20 meters. It is nothing but 20 meters. So the value written on the chain handle is what? 20 meters. But tell me what they are saying. They are saying that it is 20 centimeters too short. 20 centimeters too short. So tell me, what is the actual length of the chain on the field? Is it 20? No. It is 20 minus 0.2 meters. Too short, na? So 20 minus 0.2. So then what is the answer? It would be 19.8. The chain is actually 19.8. In the handle it is written 20, but actually the chain is only 19.8. What is the measured length of the line in the field? It is 200 meters. If so, what is the correct length of the line L? It is equal to measured length into L dash by L. So measured length is 200 into, what is L dash? L dash is nothing but 19.8 divided by L is 20. So what is the answer? It will be 10 into 19.8. You should get the answer as 198 meters. That should be the correct answer. Okay, so the correct answer for this question is what? It is equal to 198 meters. Okay, right. That is the correct answer. Yes. Now let us do our analysis. What did we discuss there? We discussed that when the chain is too short, here also they are saying that the chain is too short. What is the discussion we had? We discussed that if so, the measured length of the survey line will increase, right? This is the discussion. Whenever the chain is too short, measured length of the survey line will increase. So tell me, what is the measured length here? The measured length here is 200 meters, but what was the correct length? It was only 198. So that particular survey line was only 198 meters in the field. It was only 198 meters in the field. But as your chain is too short, when you measure it, you are getting the value as 200. Exactly the same discussion we had. Measured value is 200, but only the correct value is only 198 meters. Okay. Yes. Okay. So this is a direct model of problem, right? Let us try this problem. Please try this problem. Any answers? He has given me some answers here. Yes. Now, before we start the discussion, before I start the discussion here, tell me what is the major difference between this problem and the previous problem. So let us read this. 30-meter tape was used for measuring a survey line, was found to be 10 centimeter too long after measuring distance of 2,500 meters. At the end of the day, we measured a total distance of 4,500 meters and the chain was found to be 15 centimeters too long. Calculate the correct length if the chain was exactly 30 at the start of the work. So in this problem, right, at the beginning of the work, the chain is 30. After measuring some 2,500, it is 10 centimeter too long. After measuring 4,500, it is 15 centimeter too long. So the problem is the chain length is not remaining constant. The problem with this question is that the chain length is not remaining constant. If you go back to the previous problem here, please understand the chain is too short throughout the measurement. What is the meaning of that? From starting to ending, from starting up to ending, it was 20 centimeters too short. That is the case. So here, that is not the scenario. So let us see how we can analyze this problem here. The beginning of my measurement. At the starting, what is the length of the chain? The length of the chain is exactly 30 meters. After measuring a distance of how much? 2,500 meters. What is the length of the chain? The length of the chain is 10 centimeter too long, so it is 30.1 meters. And after measuring a total distance of 4,500 meters, what is the length of the chain? 15 centimeter too long, so that is 30.15 meters. These are the data given to you. So what we need to do is we need to consider it as two intervals. Let us talk about the first interval. In the first interval, what will be the incorrect chain length? What will you take the value of L dash as? Right? Can I take it as 30.1? The answer is no. Because 30.1 is only present at this 2,500 meter mark. Right? 2,500 only now? Yes. Yes, 2,500 only. So the value of 30.1 is only valid at this 2,500 meter mark. If you look at any other point, it is not 30.1. Slowly it is increasing. So initially it is 30, after that 30.01, 30.02, 30.05, 30.08, 30.09, and it becomes 30.1. So if you are having, right, two different values at two end, what you do? Basic logic is you take the average. You take the average of these two. 30 plus 30.1 by 2. What is the value you will get? You will get it as 30.05 meters. 30.05 meters. Right. That is the L dash value. You take the average value. Right. Yes. Now, what is the measured length of the survey line? L dash in the first interval. So, what is the L dash value in the first interval? Measured length is what? 2,500 meters. Okay. What is the designated chain length? What is the value on the handle? That will never change. Value on the handle will never change. It is 30 meter only. Okay. So, tell me what is the correct length L in the first interval? What is the correct length? Measured length, that is 2,500 into L dash 30.05 by L. What's the value? What is this? Can you please tell me what is the value coming as? Very good, Srikanth Teja. Your analysis was correct. 2541.67. So this value is coming as 2541.67 meters. I'm getting this value as how much? 2541. Okay. Okay. 2504.16. How much is that value? 2504.16 meters. Right. Now do the same analysis in the second interval. Please tell me. Do the same analysis in the second interval and tell me the length of the line. Please do it. What is the value of L dash? The value of L dash is 30.1 plus 30.15 by 2. 30.125 meters. It is equal to 30.125 meters. What is the value written on the chain handle? It will remain as 30 meters. The value written on the chain handle will remain as 30 meters. value written on the chain handle will remain as 30 meters. What is the measured length of the survey line in the second interval? It is not 4,500. It is 4,500 minus 2,500. That will come out to be 2,000 meters. Okay, that will come out to be how much? 2,000 meters. Then what is the correct length in the second interval? It is 2,000 into 30.125. What is the answer? 2008.3. Right. So what is the correct answer here? L1 plus L2. So if I add this, I'll get it as 4512.49 meters. 4512.49 meters. Correct now? Yes. That is going to be your answer. Okay, so did anybody get this answer initially correct? So let me go back. 4518.33 because you have taken average data initially, that's the reason why. Everybody got 4518 only, 0.3. Okay, so I hope you understood what is the mistake that has happened here and what should be the correct approach. Okay, so this is a good problem, right? This is a good problem. Please make sure that you practice this problems. Okay, in data they have asked questions around this concept, but not with the concept where the length is vary. Direct concepts they have used last year also. Right, 22 also we had one question. Right, this concept. Right, chain was too long, too short throughout the measurement. Right, but they did not ask this particular concept where the length is varying. So this is one untapped area linkage. Right, so this is an untapped model in gate. Right, untapped model in gate. Yeah. So such untapped areas you please concentrate. That is what gate is moving towards. Yes. So that is our discussion there. Okay. Right. Now we'll move on to the discussion of errors in chain survey. Okay. With whatever concept that we discussed now, we'll talk about the errors in chain survey. Okay. So tell me, what are the sources of errors? What are the sources of errors in chain surveying? The sources of errors are same as before. We discussed in the basic concept. Natural sources of errors, personal sources of errors, instrumental sources of errors. And at the same time, I told you that we don't care about the sources of errors. Okay. Because ultimately, at the end of the day, if you want to apply corrections will be applied only on the basis of what? Only on the basis of the nature of the error. What are the three types of errors that we have? Mistakes, systematic errors, and our accidental or our compensating errors. Mistakes can be avoided in the field itself. You go and remove the confusion from the mind of the people. Mistakes can be avoided. Yes. The remaining two we need to discuss. That is the systematic errors. We need to form the mathematical equations for them. Followed by the second type of error is what we call it as the systematic or cumulative errors. Sorry, second type of error is what we call it as the accidental errors. We'll take examples of that. Okay. So you please listen here. Systematic or cumulative errors. What do you mean by systematic or cumulative errors? Like they follow a definite physical or a mathematical relation, right? And we can frame the values for these errors. Look at the first error. The first error is what we call it as error due to standardization. What do you mean by error due to standardization? It means that the chain is not of standard length. What do you mean by error due to standardization? It means that the chain is not of standard length, right? So why is the chain not of standard length? Because the chain is either too long or too short, right? It can be of any reason. Yes. So tell me, we just need complete the description. If the chain is too long, what is the error? If the chain is too long, measured length of the value increases, the error is negative. What if the chain is too short? If the chain is too short, measured length of the line increases and the error is positive, right? So the error due to standardization is maybe positive or maybe negative. Can it be like too short and too long at the same time? No. So either it is positive throughout the measurement or negative throughout the measurement. It cannot be too short and too long at the same time. Next one is error due to temperature. What was the standardization temperature? Do you remember? What was the standardization temperature? Standardization temperature was 20 degrees. What if your field temperature is more than 20? What will happen? Chain becomes too long, right? Error becomes negative. What if the temperature is less than 20? If it is 10 degrees Celsius, chain contracts. Chain becomes too short. Error becomes positive. So the error due to temperature is cumulative and it can be positive or negative. What was the standardization pull you applied? Standardization pull is 80 Newton. If you apply something like only 60 Newton, will the chain be fully stretched? No. We know that under zero pull, chain is not equal to 20 or 30. It is less than 20 or 30. Under 80 Newton only, it becomes 20 or 30. So if you are applying less than 80 Newtons in the field, your chain will be definitely lesser than 20 or 30. The error becomes positive. The chain is too short, the error becomes positive. What if you apply 100 Newton? Chain will be elongated. The chain is too long, the error becomes negative. Right. Now please remember, the error due to slope, the error due to bad ranging, right, misalignment, as well as the error due to sag. All these errors are cumulative and all these errors are always positive. All these errors are always positive. Why they are positive? We will discuss in the next discussion. Right? We'll discuss it pretty soon. So error due to slope, error due to sag, error due to bad ranging, these are all cumulative and they will always remain positive. The errors are positive. So if the errors are positive, what will be the nature of correction? Negative. Okay. So the correction for slope, the correction for bad ranging, like these particular values are always going to remain what? They're always going to remain negative. Okay. Yes. So that is about the different systematic or cumulative errors. Please remember, we studied this in the first chapter. Cumulative errors are always proportional to length of the lines. Cumulative errors are always proportional to length of the lines. Right. The next error that we have is our compensating errors. Right. And remember, these compensating errors are always proportional to what? Square root of length of the lines. Always proportional to square root of length of the lines. Okay. Yes. What is the example of compensating error? See, the best example is something known as variation in pull. What do you mean by variation in pull? See, in the previous discussion, we had this pull discussion here. The third one is nothing but our pull discussion. So here, the idea is, in this third one, the idea is that, you see, we are applying a pull. The third one, the idea is, we are applying a pull constantly more than 80, or we are applying a pull constantly less than 80. Okay. All throughout the measurement, I am applying 100. Okay. Or all throughout the measurement, I am applying something like 60. That is the discussion here. But what is the discussion here? Right. So here, there is variation in pull. So you imagine your chain surveying lab. Okay. You go to your chain surveying lab. Generally, it's the chain survey or the surveying lab starts at morning 10 o'clock in your college. Yes, sir? Yes. So imagine you are in your lab morning 10 o'clock. You are divided into groups of 5, and every group will be given one chain. And you see, in any one of the group now, there will be one person who goes to gym. There will be one fellow who goes to gym. You give the chain to him in the morning. After the entire breakfast, right, morning 10 o'clock, he's having full energy. You give the chain to him. He will roll up his sleeve and he will pull with the entire force, showing off his biceps. He'll say, "I look at my biceps now." Okay. So what is happening to the chain during this time? Since he's applying the entire force that he can give, you are going to get pull greater than 80 Newton, something like 100 or even 200 Newton and all. Yes. But the problem is the chain surveying lab is for 3 hours. You go in at 10 o'clock, you can come out only after 1 o'clock, only by 1 o'clock. That means by lunchtime only you come out. By lunchtime, by 1 o'clock, all the breakfast is gone. Now our gym friend is very tired. You give the chain to him, he will not even hold it properly. He will just hold it with a single hand and say, "Arey man, you take the machine." Correct now. So now he is not applying with enough pull. So morning he was applying something like 100, 110 Newton of pull, right? Making the chain too long. By afternoon, he's not even applying the required 80 Newton. He's only applying 60, 40 Newton only he's applying. So what happens? The chain will not be fully stretched. So the chain will be too short. So in the morning, the chain is too long. In the afternoon, it is too short. So morning, the error is negative. Afternoon, the error is positive. So what happens? We assume that it will cancel. That is variation in pull. So the pull you are applying is not constant. It is varying. Initially high, after that less. So like increase, decrease, positive error, negative error. We assume that it will get compensated. It will get balanced. That's it. That is what we call it as variation in pull. Okay. Similarly, the second one is what we call it as incorrect holding or marking of chain. Incorrect holding or marking of chains. Okay. So if this is my arrow in the ground, the chain handle should come exactly and touch the arrow. But if you are not properly holding, there is a possibility that first time you may increase your length like this, or second time you may not bring it up to here. So this is measured length too long, and this is measured length too short. Okay. Yes. Both of them can result in a compensating error. We are going to assume that they will get compensated. That's it. So we need not numerically, investigate any equations for compensating error as of now. But in chapter number 30, we'll see a completed discussion on this accident errors. Yes. Now please remember the points that we discussed. Cumulative errors are proportional to length of the lines, and compensating errors are proportional to square root of length of the line. This particular point we will see in chapter number 30. This particular concept we will see in the upcoming discussions. Okay. So that is the discussion regarding the different errors in chain surveying. Now we will move on to our numerical value of the corrections. We know the errors. We need to find the numerical value of these corrections one by one. Okay. So I hope that discussion is clear. Right. So let us move on to the tape corrections. So this is again an important area in gate examination. Last year there was a question on this particular tape correction. Okay. This tape correction was combined with the fact that the chain was too long or too short. Right. Chain, correction. One chain correction was combined with the fact that your chain was too long or too short. Yes. Let us try and solve this corrections. Okay. So what was the first type of error that we discussed? What was the first error that we had? The first error that we had is nothing but you see, like we are talking about obviously compensating errors only. Cumulative errors only. First error is error due to standardization. So the first correction would be correction for standardization. Correction for standardization. I will write short form. You cannot write short form. Okay. You are not supposed to write short form, but I can do. Yes. What is the formula for correction for standardization? It goes like this. Correction for standardization is equal to measured length into L dash minus L divided by L. I hope you remember the parameters here. L dash is the measured length. Right. Capital L dash is the actual chain length. Sorry, incorrect chain length. Or the actual chain length. Yes. And capital L dash is the designated chain length. There is a value written on the chain length. So tell me something. What is the meaning of this? L dash is greater than L. But now L dash is the actual length of the chain in the field. L is the value written on the chain handle. If I write L dash is greater than L, what is the meaning? But now, is the chain too short or the chain too long? Tell me. Yes, very good. So this condition will indicate that the chain is too long. Right. Now, if the chain is too long, what happens to the error? If the chain is too long, measured length of the value increases. Right? Measured length of the value decreases. The error is negative and the correction is positive. Yes or no? Yes. Tell me, if L dash is greater than L, inside this value, inside the bracket, what is L dash minus L? It is a positive value. Correct. If L dash is greater than L dash minus L is a what? Is a positive value. Similarly, what if L dash is less than L? If L dash is less than L, the meaning is the chain is too short. The meaning is the chain is too short. The error is positive and the correction is negative. So if L dash is less than L, what is L dash minus L? It's a negative value. You'll get the correction also negative. Okay. So this is how you remember your formulas. Don't mug up. There should be some concept that you should associate with every formula. So if you try and analyze that concept here, you don't have to mug up. You don't have to mug it up. Right. So if you mug it up, the problem is you go to your exam hall, you'll have it out that it is minus L or plus L. But if you know the concept about what's happening, that particular mistake will not come. Yes. So that is our error due to standardization. Similarly, the next error that we have is, or next correction is correction for temperature. Correction for temperature. Yes. So what is the correction for temperature given? It goes like this. Correction for temperature is equal to alpha into Tm minus T naught into M. What is the formula for correction for temperature? Is equal to alpha into Tm minus T naught into M. Right. So what is alpha? Right. Alpha is nothing but coefficient of thermal expansion. Coefficient of thermal expansion. What is Tm? Temperature at measurement. Right. What is T naught? Temperature at standardization. Okay. And this is the formula. So this is the formula how it looks like. You can do the same analysis. Okay. What if Tm is greater than T naught? Can you imagine what will be happening if Tm is greater than T naught? Tm is greater than T naught means, right, the chain is too long. Measured temperature in the field is greater than the standardization temperature means the chain is getting elongated. The chain is getting elongated. Then what happens? The chain is too long, measured length of the value decreases, negative error and positive correction. Yes or no? So as you can see, if Tm is greater than T naught, obviously Tm minus T naught is a positive value. Same thing, same analysis. See, this is nothing but alpha into delta T12. Change in length is equal to alpha into delta T12. Same thing only. Yes. Okay. Next step. Third one is your correction for pull. Correction for pull. Okay. Right. So what is the correction for pull? What is the formula? It goes like this. Correction for pull is equal to this formula also you know. It is Pm minus P naught, right? Pm minus P naught into L divided by AE. Yes or no? Do you know this formula? Yes. Delta L is equal to P into L by AE from your strength of material. We know Young's modulus is equal to stress by strain. From that relation we can derive this. Yes or no? Yes. So let us identify the parameter here. So what is Pm? Pm is equal to pull at measurement. Pull at measurement. Right. What is P naught? Pull at standardization. Pull at standardization. What is A? A is the cross-sectional area. Cross-sectional area. What is E? E is Young's modulus or modulus of elasticity. Yes. Okay. You can, if you wish, you can do the same analysis. Right. If Pm is greater than P naught, what is happening? Pull at measurement greater than pull at standardization means chain will be elongated. Measured length decreases. Error is positive. Error is negative. Correction is positive. P minus P naught will be a positive value. Correct? Huh? Yes. So this is our correction for. Now the fourth one is the important one. See, first 2, 3 are very simple only. Right. Fourth one is slightly different. What is that? That is the correction for pull. Sorry, correction for slope. Okay. Correction for slope. Right. Now please remember the error due to slope is always positive. So correction for slope is what? Always negative. It is cumulative, but it is always negative. Okay. Yes. Let me explain this condition. Please listen carefully. Okay. Please listen carefully. So you imagine that your ground is sloping like this. Right. You imagine that your ground is AB and this ground is sloping like this. So tell me something. In this sloping ground, whenever I put a chain, will I get the sloping distance AB or will I get the horizontal distance, right, AB dash? Tell me. In this particular ground, sloping like this, if I put my chain on the ground, what will be the measured value? Will it be the sloping length AB or the horizontal distance AB dash? Obviously, the chain will give you the value of AB. But tell me, is that the distance that you want? No. The correct distance that you want is AB dash. You wanted to know what is the correct horizontal distance between A and B, that is D. But as the ground is sloping like this, what will you get? You will get the sloping length as L1. You will get the sloping length as L1. So L is the measured length, D is the correct length. Then tell me, what is the error? How do you calculate error? Error is nothing but measured value minus correct value. Yes or no? This is how you calculate error. Error is what? Measured value minus correct value. What is the nature of this error? What is the nature of this error? Look at this sloping length L and look at the horizontal distance D and tell me who will be greater. L is greater or D is greater? L is greater or D is greater? There is no doubt L is greater than D. In fact, L is always greater than D. There will be no condition in the world where the sloping length between the 2 points is less than the horizontal distance between them. It can never happen. So, you see, whenever the slope is coming into picture, the measured value will always be greater than the correct value. The measured value, L, will always be greater than the correct value d. So then what is the nature of the error? If the measured value is always greater, the error is going to be always positive. So this L minus d error is going to be always positive. But tell me, what if I multiply this particular positive error with a negative sign? What if I multiply error with a negative sign? Error multiplied with a negative sign is what we call it as correction. So tell me, what is the correction for slope? Correction for slope is equal to L minus d, but that is the error. Multiply that with negative sign, you get correction. So correction for slope is L minus d, but represented with a negative sign. Let us assume that the slope angle here is equal to theta. Let us assume that the slope angle is equal to theta. Then how can I replace the value of d? D will be equal to L cos theta. Then how can I replace the equation? I can replace the equation as L minus L cos theta or L into 1 minus cos theta. Again, the sign is always negative. Again, the sign is always what? Negative. Right? That's it. Now, let us assume that the difference in elevations between the point B and H, difference in elevation between them is given as H. So B and A, the difference in elevation is H. Then how can I replace the value of D in the first equation? I can replace the value of D as L minus, what is D? Under root of L square minus H square. Again, right, the sign has to be negative. Now, if I take the binomial expansion of L minus under root of L square minus H square, the binomial expansion of this will be equal to something like this. I'll give you the final equation. It goes like this: H square divided by 2L plus H raised to 4 divided by 8L cube, right? Plus etc. 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 Now, please understand, compared to the L value, H value will be very less. In chain surveying, we cannot have H value very large because, right, we are choosing chain surveying in only very flat ground. Right. So in that scenario, H value cannot be too large because if the difference in elevations are too large, then chain surveying is ruled out. So H is very small compared to the horizontal distance. So this H power 4 by 8L cube will be an even smaller value. So what we'll do? We will neglect the higher powers. We will neglect. Right. So because the value is very less. So if I neglect this, what happens? The correction for slope becomes approximately equal to what? H square becomes approximately equal to H square divided by 2L. What is the sign? Always negative. H square divided by L. What is the sign? The sign is always negative. That's it. So that is the correction for slope. That is the correction for slope. So please understand, there are in fact 3 to 4 formulas for correction for slope. What is the correction for slope? When the sloping length and the horizontal distance is given. When the sloping length and the horizontal distance is given, correction for slope is equal to L minus D. What is the correction for slope when the sloping length and the slope angle is given? L into 1 minus cos theta. What is the correction for slope when the sloping length and the difference in elevation is given? Right, H square divided by 12. These are the formulas. Okay. So depending upon which data is provided to you, you can use the correct formula to find the answer. Okay, now? Let me just try and give you a small problem here. If the 30-meter end of a chain was held up 1 meter too low, right? The correction for slope is dash. Slope is dash. Okay. Tell me the answer. Any answers? Yes. Okay, so I'm getting the answers here. So you're saying that the chain is held at 1 meter below. So let us look at the solution. See, truly speaking, this is how the chain should be held. If this is 0 meter, this is 30. But what they're saying is this particular point is held at what? 1 meter below. This is held 1 meter below. So the 30-meter end should come here, which means the tape is like this. So yes. So now they're asking you for the correction for slope. What is the formula you will apply? The formula that you can apply is H square divided by 12. The sign is always negative. So here it is 1 square divided by 2 into 30. So the answer is minus. And what should be the sign? The sign should be negative. So the answer is minus 1 by 6. That should be the correction for slope. Correction for slope is equal to what? Minus 1 by 6. Yes. You can write it as minus 0.0166. 166. Okay, that's correct. Okay, right. Let us move on to our next correction here. That is correction for bad ranging or misranging. Number 5. Okay. move on to our next correction here. That is correction for bad ranging or misarranging. Number 5. Correction for bad ranging, or this is also known as misarrangement. Bad ranging and misarrangement. Okay? Yes. So what is meant by ranging? Please remember. So if this is your survey line, say PQ. Okay? If this is your survey line, and like this. Yes. So this is your survey line PQ. What do you mean by ranging? Ranging is nothing but the process of finding. Ranging is nothing but the process of finding an intermediate point somewhere around here like this as R, right? So that you can measure the distance as D1 plus D2. So that you can measure the distance as PR plus R2 or D1 plus D2. But what has happened here? Bad ranging has happened. That means your point R was not in the survey line PQ, was not along the survey line PQ, but you are getting the point R somewhere around here like this. That is the incorrect question. So you see what happened? Point R is misaligned. Point R is misaligned like this. So due to this particular misalignment, tell me what will be the measured length of the survey line? Instead of getting PR, you will get PR dash, and instead of RQ, you will get R dash 2. Instead of RQ, you will get what? R dash 2. So you will be getting L1 plus L. That is the measured length. So tell me, what is the error in the first half? The error in the first half is L1 minus D1. The error in the first half is what? L1 minus D1. Plus, what is the error in the second half? L2 minus D2. Please remember, this error is always positive. Right? This error is always positive because L1 and L2 obviously greater than D1 and D2. If I multiply that with the negative side, what happens? I'll get the correction for misalignment. Okay. Now, let me say that this particular angle is equal to theta. This particular angle is equal to theta 1, and this particular angle is equal to theta 2. Right? So then what is the value of L1? Right? What is the value of theta 1? Like, how can I replace D1 as? What will be the value of D1? D1 will be L1 cos theta 1. So I can take L1 common outside. L into 1 minus cos theta 1 plus L2 into 1 minus cos theta 2. What is the sign? The sign is negative. The sign is negative. Okay, yes. Now, let me say that the amount of displacement, the amount by which misalignment happened is D. So if I know L1 and D, how can I replace capital D1? Capital D1 can be replaced as minus of under root of L1 square minus D square plus L2 can be replaced as D2 can be replaced as L2 square minus D square. What is that? That is negative. Yeah? Yes. Now, if you remember, these formulas looks exactly the same as our slope correction. This looks exactly the same as our slope correction. So what will be the correction for slope? The correction for misalignment will be, how did I replace this value? I will replace the first term as you see, h square divided by 2L1 plus h square divided by 2L. Like the sign is always obviously negative. Yes. This is how the formulas can be approached. Now listen carefully. What if the misalignment is happening exactly at the center? If the misalignment is happening exactly at the center of PQ, what will happen to this L1 and what will happen to this L2? L1 becomes equal to L. Correct now? The misalignment is exactly at the center. L1 becomes equal to L2. L1 becomes equal to L2. So then what will happen? So you see, if misalignment is at the center, what happens? What happens is L1 becomes equal to L2 becomes equal to L. Like this. L1 becomes equal to L2 becomes equal to L. Then what is going to be my correction for misalignment? Correction for misalignment is equal to, right? Sorry, that is D now. Not H here, okay? D square. Okay. What will be the correction for misalignment? The correction for misalignment will be, right, D square by 2L plus D square by 2L. It will be D square by L. The sign is negative. That becomes my question. So please read the question carefully. What kind of parameters they are mentioning? Based on that, you select the formula. That's it. That is the correction for misalignment. Okay. Yes. Let us take a small numerical here. So please write the answer. Okay. So please, the correction for misalignment. Okay. Yes. Let us take a small numerical here. So please write the answer. Okay. Correct? Horizontal distance is dash. Please solve this. Okay. I'll give you 2 minutes. Please try this problem. Any answers? Okay. So let us see how to solve this. First and foremost, right, let us see what is the formula is. So the misalignment is at the center. Okay, misalignment is at center. So what is the formula? The correction for misalignment is minus of d square divided by L. What is d here? D is nothing but 1 meter. Okay. D is given as 1 meter. What is L here? Please understand. This was the misalignment of 1 meter. Right? Whenever misalignment is there, what happens is L1 becomes equal to L2 becomes equal to L. Okay. So in the question, the measured length is 60 means what? L plus L is equal to 60. Right? Right? So in the question, right, they are saying that this is 1 meter. 1 meter means what? Like this is the misalignment L1 here. This is the measured length L2 here. L1 becomes equal to L2. Right? So the measured length is 60 means L plus L. 2L is equal to 60 meter or L is equal to what? 30 meters. L is equal to 30 meters. Now tell me what is the correction for misalignment? We minus 1 square by 30. So your correction for misalignment is minus 0.033 meters. Right? That is the correction for misalignment. Finally, they are asking me for correct length. Correct length is nothing but measured length plus correction. Measured length is 60 plus correction is minus 0.033. So you should get the answer as 59.967 meters. Your answer should be 59.967. Right, so this is the answer that you're supposed to get. Right, so the problem is most of you will make a mistake here that the L value is equal to 60, but that's not right. L value is given, 2L value is given as 60. You should understand. 2L value is given as 60. Or becomes 30 or the correction becomes minus 1 by 10. Right, now also they are asking me for the correct horizontal distance. Correct length is equal to what? Measured length plus correction. Apply this, you should get the answer as 59.967. I hope this particular problem is clear. Yes or no? Right, please yes or no? Yes. Okay, right. Let us move on to our sixth correction here. That would be nothing but correction for star. Right, our sixth correction is, like, remember, this is also always negative. This correction is also always negative. Correction for slope always negative. Correction for misalignment also negative. The sixth one is correction for star. And that is also always negative. Right. Now, what do you mean by sagging? See, if you look at your electric transmission lines, you'll observe that they are always sagging. So, if you imagine that this is the side of the road, okay. If you imagine that this is the side of the road that you're having, this is one, like this. Okay. So, this is one of your transmission lines here. This is another transmission line like this. In between them, the lines will always go like this. In between them, the electric transmission lines will always be like this. Yes. That condition is what we call it as sagging. Right. So, where the transmission lines are like this, we expect it to go like this, but it does not go due to self weight. It will align in a direction like that. So, no, yes. That condition is what we call it as sagging. Yes. Now, why does our chain sag? Generally, we put our chain on the ground. So, if the chain is supported by the ground, how does it sag? Please understand, it is not necessary that every time I will be putting the chain on the ground. If my ground is highly elevated like this, if your ground is highly broken like this, difference in elevations are not there, but it is broken. So, at that point, to measure the distance between points A and B, what we can do is, we can drive some wooden pegs here, or even wooden bolts here, and we can expect the chain to be kept to horizontal lengths. Okay, we can get some wooden pegs like this, and we can try and put our chain horizontal in this fashion. Right, we can try and put our chain horizontal in this particular fashion. But due to the self weight, will the chain go and will go horizontally? No, definitely not. The chain will align in the shape like this. Due to the self weight, the chain will align in a direction like this. So this will be the actual length that you want, L. Right? This is the actual length that you get. But the horizontal distance that you want is D. You wanted to get D, but you are getting it. Who is greater? L is greater. Measured length is greater than the corrected D. So the error is positive and the correction will be always negative. Please remember, this resulting shape of my chain is what we call it as catenary. What we call it as a catenary shape. It's what we call it as a catenary shape. Okay? Yes. Now, why is this important? Because sometimes in your numerical they'll say a chain was kept in catenary. What do you mean by that? Sagging direction needs to be applied. Right. Now, whenever you see the chain sagging like this, what is our first reaction? Our first reaction is to apply pull from both directions and try and make the chain horizontal. This is the first common reaction. Whenever you find the chain sagging, we have a tendency to apply pull from both sides and make the chain horizontal. Now, this will definitely decrease the amount of sagging that we see, but will not completely eliminate it. Right. So, due to the self weight the chain will sag, the pull will try and slightly reduce. So, I can write like this: the correction for sag is a function of both the self weight of the chain and the pull up. So, this is calculated as total weight of whole square into total length divided by 24 p square. Remember, the sign is always negative. So, weight is function. As weight is increasing, sagging will be more. As you are applying pull, if pull is there, sag will come down. You can see that from the equation. So, what is W here? W is total weight. Total weight. Small w is what? Weight per length. If I say that small w is weight per length, what is capital W? Weight per unit length. Weight per unit length is total length. We can calculate it. And what is P here? P is nothing but the pull up weight. P is nothing but the pull up weight. Right. if you want to reduce the sag more, if you want to reduce the sag, effectively, then what should I do? If you want to effectively reduce the amount of sag coming here, what should I do? Should I increase the pull? The answer is no. Should not increase the pull, because if you increase the pull too much, what will happen is the effect of pull becomes more and more. The effect of pull becomes more and more and more, and what happens is like the chain becomes too long. Right? So increasing pull is not the correct solution to solve or to reduce the amount of sag. What you do is like you reduce the length. Reducing weight is also not an equation because weight is a measure of strength. Reducing weight is ruled out. Increasing pull is ruled out. So what you do is you reduce the length. By reducing length, what you're meaning is you give more number of support. Right? Decrease the span of my chain. Like so that what happens? My chain will be sagging only lengths. The chain will be sagging only lengths. Right? So do you remember? Have you ever noticed after washing clothes when our mother will put the cloth on that particular rope? What happens? The rope will sag, and sometimes the cloth will come and touch the ground. What mother will do? Mother will take one very long wood, one piece of wood she will take, and she'll give one support at the center. Correct? Right? So she'll take one stick and give one support at the center. That's the basic idea. So give supports. The effective sagging can be reduced. Yes. Now this space that you see between two supports, this is what we call it as bay, or even you can call it as span. So let us assume that there are n number of bays. N represents the number of bays or the number of spans. How can we calculate that n value? The n value can be calculated as number of supports minus 1. So in this figure, how many bays you see? How many supports you see? 1, 2, 3, 4 supports are there. How many bays are there? 3. So 4 minus 1 is 3. So number of supports minus 1 will give you the number of bays. Now, what will be the total correction for sag? The total correction for sag will be equal to total weight, the whole square into total length, divided by 24 into t square n square. The sign is always negative. T square n square, the sign is always negative. So this is how you find out the amount of sag. This is how we find out the correction for sag. So you see, as n increases, as the value of n increases, the sag correction decreases. Weight did not change, length did not change, weight did not change, pull did not change, but the effective sag is going to decrease. Okay, L becomes the total length. L is nothing but the total length from here. That's it. So this is the correction for sag. Okay, yes. Now, when I told you that increasing the pull is not the correct way of reducing the sag, right? Yes or no? Yes. Why? Because if you increase the pull, the effect of pull correction starts to increase. So the question that we should ask ourselves is, so what is the actual pull, or what is the limiting amount of pull I can apply in this field? Okay, so because you don't know how much pull you should apply, so that the pull is not affecting too much. Okay, so that limiting length of pull that you can actually apply on the field is what we call it as normal tension. So the seventh one is what we call it as normal tension. So what happens? See, normal tension P. Normal tension we call it as P. When you apply this normal tension in the field, what is going to happen is the pull correction and sag correction will balance each other. Okay, if you apply the pull equal to normal tension in the field, what is going to happen? The amount of pull correction that you are going to get will be equal to magnitude wise equal to the amount of sag correction. Now since this pull correction is obviously greater than standardization pull, so what is going to happen is positive pull correction you will get, negative sag correction you will get. If you add them, the total error becomes equal to 0. This is what is going to happen. Okay, so I can write like this. What is this? This is the pull at which correction for sag becomes equal to correction for pull. Okay, pull at which sag correction becomes equal to pull correction. That is what we call it as normal tension. So let us equate. So what is pull correction? Right? What is pull correction? Pm minus P naught into L by AE. One second. Okay. What is pull correction? Pm minus P naught into L by AE is equal to what is sag correction? Total weight of whole square into total length divided by 24 P square. When they are equal, see they become equal only when the pull applied is normal tension. So from here I can cancel this L, right? And then I can write Pn square is equal to how much? Pn square is equal to, right? You can see that here will be equal to W square into AE divided by 24 into Pn minus P naught. Right? Now if you take square root of this, you get the value of normal tension as you see. What is under root of W square? W. A becomes under root of A. What will be the value in the denominator? The value in the denominator will be under root of Pn minus P naught. But there is 1 by root A 24. That 1 by root 24 will go to numerator as 0.204. So that 1 by root 24 will go to the numerator as 0.204. Yes. So this becomes the equation for your normal tension. This becomes your equation for what? Normal tension. Okay. If you observe, the normal tension is present, right? The Pn value is present both in the LHS and in the RHS. So if you want to solve this, you need to go with the trial and error method. In gate calci also, you cannot solve this is a third order equation, cubic equation. You will not be able to solve this cubic equation in your gate calci. So if at all you get a question, chances are very less. But if at all you get a question, right, you have to solve it with the trial and error method. That's it. So that is our normal tension. Okay, yes. The last correction that we'll discuss here is the one last correction that let us finish that. That is what we call as reduction to mean sea level. Is what we call it as reduction to mean sea level. Okay. So what is MSL? MSL is nothing but mean sea level. Why we want to reduce the length to mean sea level? Reduction to mean sea level means whatever length we have measured, we are reducing it, we are projecting it down to mean sea level. Why we need to do that? Right? Because you see, right, our Earth's surface is highly undulated, no doubt in that. The Earth's surface is highly undulated, yes. Right? But when we make the globe of the Earth, just think about this. When you make the globe of the Earth, the globe is an exact sphere, correct? It's a very, very smooth surface. So the actual Earth's surface is undulated. That means we are having ground above mean sea level, we are having ground even below mean sea level. But when we prepare the ground, the globe, everything is represented in a one sphere. Why or how? Because what we do is, we will measure all length above mean sea level and below mean sea level, apply this correction, and project them down to mean sea level. So what happens? All length are now measured on the mean sea level. Now I can represent it as a smooth uniform surface. I can represent it as what? Smooth uniform surface. So to do this, what is the formula? The formula will go something like this. The reduction to mean sea level is equal to L into H by R meters. What is L? What is H? What is R? Let us understand. So you imagine this is your mean sea level. You imagine that this is your mean sea level, and you imagine this is a ground AB. This is a ground AB that you are having, like above the mean sea level. Like what we are trying to do is, we are trying to project this particular ground onto the mean sea level. We are trying to project this particular ground onto mean sea level. Okay, like this. So when you are projecting it down, what is the correct length that you want? the correct length that you want is D. The correct length that you want is D. Okay, na? Yes. What is the measured length L? So look at this. The measured length is L, right? Right, and the correct length is D. Where is this line AB? The line AB is h units above mean sea level. The line AB is h units above mean sea level. So the line is above the mean sea level. Length of the line is L. The correct length that you want is D. So please tell me, when you project this line AB onto the mean sea level, when you are projecting this line AB onto the mean sea level, what is the sign of the correction that you need to do? Please tell me. Who is greater here? L is greater or D is greater? From that discussion there, L is greater or D is greater? L is greater than D, right? So as the line AB is above the mean sea level, right, the measured length L is greater than, right, the greater than the correct distance. So when I project it down, what should be the correction? The correction should be negative. Understand? Right? Because you see, AB is greater. If I want to reduce it down to mean sea level, I need to give a negative correction. Understand? Similarly, what if you are having another line say CD, like this is another line I'm having CD. Where is this line? You can see this line is below mean sea level, h units below mean sea level. What is the measured length of the ground to CD? That is L. When I project it down or project it up onto the mean sea level, the correct distance you want is D. So tell me, who is greater? L is greater or D is greater? Clearly, L is less than D or D is greater than L. So when I'm giving this particular correction, what will be the sign of the correction? The sign of the correction will be positive. L measured length is less than the correct distance D. So what is error? L minus D is negative. Error is negative. So what kind of correction I should give? Positive correction. Yeah. So please remember, this particular correction may be either positive or maybe either negative. When is this correction positive? When h is measured below mean sea level. The line is lying below mean sea level. And when is this correction negative? When my line is lying above mean sea level. So h is measured above mean sea level. So this is the formula. Now, do you need to mug up the sign here? No, you don't have to mug up the sign. You just need to have your logic. Use your logic. If the ground is above mean sea level, and if I'm projecting it down, am I increasing the length or am I decreasing the length? I'm decreasing it. So if the ground is above mean sea level, I need to give negative correction to decrease it. That's it. Similarly, if the ground is below mean sea level, when I try to project it on top of mean sea level, I am increasing the length or decreasing it. I'm increasing. So you need to give positive correction. So above means, right, you give negative correction. Below mean sea level means you give positive correction. That's it. So use your logic there, right? Then you need not mug up anything. So h is nothing but the height measured above or below mean sea level. And what is r? R is nothing but the radius of Earth. What is r? R is nothing but the radius of Earth. Okay. So the rest of the values are mentioned in the figure. L is the measured length, R is the radius of the Earth, and h is the height measured above or below mean sea level. That's it. So with this, our tape corrections are completed. Okay. So that's it, guys. So that is it for today. We'll stop here. Okay. Last 5 minutes, we'll take notes. So today we'll start with our next discussion here. That is, what are the different instruments used to set out right angles? Yeah, that is our next discussion. Right, let us begin. Okay. So are you familiar with any instruments that are used to set out right angles? Yes or no? Obviously, you will know about our cross-staff. Okay. First and foremost instrument is nothing but cross-staff. Okay. What are the different types of cross-staffs that we have? We have open cross-staff that can give me only 90 degree. We have French cross-staff that can give me 90 and 45 degree. Followed by we have the adjustable cross-staff which can give me any angle. Yes. The next instrument that we have is what we call it as an optical square. Okay. The next instrument that we have is an optical square. The third one is a modified version of the optical square. We call it as the prism square. Modified version known as the prism square. Okay. And the fourth one is what we call it as a sight square. Okay. So these are the different types of instruments that we have. We've already studied about cross-staff. We will now study about optical square followed by the prism square. Sight square is not very important for us. This lister was a previous year question. Okay. This particular lister was a previous year question. And so this was a PYQ from ESC. Very recently they asked them which among the following instruments will be used to set out the right angles. A, B, C, D they have given. Basically, if you know this list now, you can easily find out the answer for that. Okay, yes. So let us begin our discussion here. Right. So let us see how the optical square is going to look like. Okay. One second. Yes. So this is our instruments used to set out right angles, and the first instrument that we have is our optical square. How does the optical square looks like? Right. It has a circular shaped body like this with 3 openings. Okay. The optical square will have a circular shaped body consisting of 3 openings. The first opening is what we call it as the eye aperture. Right. That means the observer's eye will be there. Right. Now inside this particular instrument, we will be having 2 mirrors. Right. In that, the first one is what we call it as the index mirror, shown like this. That is fully silver. And the second one is our horizon mirror, which is only partly silver. So the first mirror that we have, that is your index mirror. Opposite to the index mirror, you can see that there is an opening. That opening is known as the index aperture. Right, that opening is known as the index aperture. The partially silvered mirror is what we call it as the horizon mirror. X, and opposite to that horizon mirror, we have the horizon aperture. But very important point that you need to remember is the angle between these 2 mirrors are always 45 degrees. Please remember, the angle between these two mirrors are always equal to 45 degrees. Now, what is the working principle? This angle is equal to 45 degrees. Okay. What is the working principle of the optical square? Please remember, the optical square works on the principle of double reflection. It works on the principle of double reflection. Okay. So, what do you mean by this double reflection? It means that whenever a light ray enters this particular instrument, whenever a light ray is going to enter in this particular instrument, it will undergo two reflections. It will undergo two reflections. How many? After the second reflection, if you look at the final reflected ray, it will make an angle of 45 degree into 2, that is 90 degree with the initial time. Let me try and say that. The principle of that particular instrument is double reflection. So what do you mean by double reflection? A light ray that is entering the instrument will undergo two reflections, one from the index mirror, one from the horizon mirror, such that the final reflected ray will make an angle of how much? 90 degrees with the initial ray. Okay, so you see this, two reflections, okay, from two mirrors kept at 45 degrees to each other. So that what happens? Final reflected ray becomes 90 degrees. Final reflected ray becomes 90 degrees. That's it. So this is the working principle of the optical square. This is the working principle of the optical square. Yes or no? Yes. Let us see how this particular instrument works. So please understand, if this is a survey line PQ, this is P, this is Q, right? And you are having a detail here, say R. You are having a detail here R. And you need to put a perpendicular offset towards the point R. Yeah, you are trying to put a perpendicular detail toward the point R. Let me represent R with the ranging rod. Okay, that will be better. And so, what is this? This is the ranging rod R, like this. We will try and represent the ranging rod with a perpendicular like this. So we are trying to. This is we are trying to put a perpendicular offset towards R. Now, the perpendicular offset should be set out from the point O. But the question is, where is point O? Is the point O here? Is it here? Is it here? Is it here? That is what we don't. So by using the optical square and moving the optical square along the length of the line PQ, we can say where should be, or we can find out where the point O should be. What is point O? Point O is the foot of the perpendicular. Point O is the foot of the perpendicular. So this optical square will help us find where should be the foot of the perpendicular. Yes. Let us look at the working. Okay. So as I told you, this is my survey line PQ. This is the point R, and this particular point represents the foot of the perpendicular. Now, how will I ensure that my instrument is at the foot of the perpendicular? Let us see what should happen. Okay. So, if the instrument is kept at the foot of the perpendicular, what will happen is the light ray coming from R. If the instrument is kept at the foot of the perpendicular, the light ray coming from R will enter the instrument like this. Through the index opening or the index aperture, light ray will enter the instrument. It will hit the first mirror, that is the index mirror. It will undergo first reflection like this, and it will hit which one? It will hit the silvered portion of the horizon. Okay, it will hit the silvered portion of the horizon mirror and undergo the second reflection like this. Now tell me, what is the angle between the first reflected ray and the final reflected ray? It is 90 degrees, right? So that is the working principle. A light ray coming from the entering the instrument is undergoing two reflections from two mirrors kept at 90 degrees to each other. So tell me, when the observer is looking through this particular point here, can you see the ranging rod R? Yes or no? Yes. You can definitely see the ranging rod R. Okay, the observer can definitely see the ranging rod R. Okay. Now, similarly, you see, whenever the observer is looking to the instrument, can he see the ranging rod Q? Yes or no? Yes or no? The answer is yes. You can definitely see the ranging rod Q also, because ranging rod Q can be seen through the unsilvered portion of the horizon mirror. Okay. So when the observer looks, you can also see the light ray coming from the unsilvered portion of the horizon mirror. Okay. So through that particular unsilvered portion of horizon mirror, you can see the ranging rod Q also. Okay. So if the optical square is kept exactly at the foot of the perpendicular, the optical square is kept exactly at the foot of the perpendicular, what should happen is, on the silvered portion of the index glass, right, you should see the ranging rod R. Okay, on the silvered portion, you should see the image of ranging rod R, right, and through the unsilvered portion of the horizon glass, you should see the image of the ranging rod Q. Please tell me, how does the point R and Q look like? The ranging rod R and Q are in the same straight line. Okay, so please understand, when you look through that particular eye aperture, right, we can see the reflection coming from the index mirror, and we can see the unsilvered portion of the horizon glass. That means the transparent part of the horizon glass. Okay, in the transparent part of the horizon glass, you should see the ranging rod Q, and on the silvered portion from the reflection, you should see the image of the ranging rod what R. So how these two are looking like? They are looking like in a single straight line, which will mean that you are standing on the foot of the perpendicular. If you are not standing on the foot of the perpendicular, R will be coming here and Q will be coming here. They will not be in the same straight line. Okay, so then you move the instrument along the length until they becomes in a same straight line. That is the correct position. Okay, right. So this is how you will use your optical square. Here, I would like to represent one more data here, that is some angles formed here. The angle that is formed with the horizon glass and the light ray coming from the horizon aperture is 120 degree. This angle you please remember. And the angle formed by the index mirror and the light ray coming from the index aperture, what is that angle? That angle is 105 degrees. So the mirrors are kept at 45 degrees to each other, and the index mirror will make 105 degree with the light ray, and the horizon mirror will make an angle of 120 degree with the light ray. Okay, that angle is also you remember. That was a previous year Maharashtra PSC prelims question. Right, when it was objective, right, that is what they asked. Okay, yes. Right. Next, we will discuss about the theory. So what is optical square? It consists of two mirrors, index and horizon mirrors kept at 45 degrees to each other. Index and horizon mirrors kept at 45 degrees to each other. Right. Next, optical square works on the principle of double reflection. Optical square works on the principle of double reflection. Okay. Next, a light ray entering the instrument undergoes two reflections from two mirrors such that the final reflected angle is 2 times 45 degree. Like 90 degree. How's that 90 degree? It is 2 times 45 degree. Now please remember, for any reason, if the angle is not equal to 45 degree, if the 45 degree angle is disturbed, instead of 45 degree, if you are getting 40 degree, what happens? Two reflections from two mirrors kept at 40 degree, the final reflected angle will be only 80 degrees to each other. Okay, now that will be a problem. So whenever you are using your optical square, one point that you need to remember is, we need to check whether the angles between them are 45 degree or not. So temporary initial adjustments are required to make sure that the two rays are at 45 degrees to each other. Right. So that is your only drawback of the optical square. That's it. Now the modified version of the optical square is what we call it as the prism square. See, the problem with the optical square is that the 45-degree angle can be disturbed. The problem with the optical square is that the 45-degree angle, yes, it can be disturbed. So to prevent that from happening, what we use is a prism. So what happens with the prism is that, you see, right, there are two sides on the prism such a way that the reflecting surfaces are at 45 degrees. So that reflecting surface is fully silvered. This reflecting surface is only, say, something like partially silvered. Okay. Now, if you look at the angles of this particular reflecting surface, what is the angle here? The angle is equal to 45 degrees. The angle is equal to what? 45 degrees. The angle is equal to 45 degrees. Okay, now, yes. Right, the angle is equal to 45 degrees. Yes. Now, what happens is, when a light ray enters this instrument, it undergoes first reflection here, it undergoes second reflection here, and then this will be the final reflection. So it works on the same principle of the optical square. Okay. Right. The only difference is that this 45-degree angle will never be disturbed. Correct now, because it is a side of a prism. It cannot change it. So that 45-degree angle will always remain the same. Okay. Right. Now, if you count the sides of this prism, there are 5 sides. Therefore, we call this as a pentaprism. Okay. Let us look at that statement here. It works on the same principle of optical square. But instead of 2 separate mirrors, it uses a prism known as the pentaprism, in which the reflecting surfaces are at 45 degrees. Okay, right. So therefore, it requires no initial adjustments as compared to optical square. Okay. Therefore, it requires what? No initial adjustments as compared to our optical square. We can use it directly. That's it. So that is the advantage of using this particular prism. So that are the different instruments that we use in our chain surveying to set out right angles. Okay. Now, the last discussion in this chapter is going to be regarding the obstacles in chain surveying. Right. If you remember the definition of chain surveying, we discussed that chain surveying is best suitable when the ground is fairly level with a few simple details to be plotted. So, if there are too many details present in the area, right, we will say that we will not do chain surveying. So, apart from that too many details, there are certain field conditions, that are, not really conducive for our chain surveying. That is not really suitable for our chain surveying. What are these obstacles we need to find out? When will I say a particular feature is an obstacle to my chain surveying? See, I will say that we have an obstacle if I cannot do ranging about that particular object, or if I cannot put a chain to that particular obstacle. Because you see, chain surveying proceeds by doing these two operations. Okay, they are, chaining, ranging followed by chaining. If I cannot do them, it means, I cannot proceed with my chain surveying. Okay, right. So you see, what are the obstacles in chaining? First obstacle is obstacle to both chaining and ranging. What do you mean by this? Obstacle to both chaining and ranging means I cannot see past the obstacle. Ranging is not possible, and I cannot put a chain through that obstacle. Can you give me an example for this? Standing on one side of this obstacle, I cannot see the other side. I cannot go and stand, in between the or inside this obstacle and see the end points. As well as I cannot put a chain through this obstacle. Give me an example for this. Yes, the correct answer is building. Okay, the correct answer is building. Okay, yes. Yes. Now, hill is not really correct. Hill is not really correct because, in chain surveying, when I say hill, it is not Mount Everest, first of all, right? And secondly, when we talk about hill and chain surveying, it is nothing but a small elevated down, like we discussed in our reciprocal level. In that particular discussion, we are able to put a chain through the we are able to put a chain through that particular small elevated hill. Yes, it is possible. Okay, but can I put a chain through a building? No, I will not go and drill a hole in my wall and put a chain through the center line of the building. No, that is random. The best possible obstacle is nothing but a big building. The next one that we have is a obstacle only for chaining. Obstacle only for chaining. What do you mean by obstacle only for chaining? Only for chaining matlab kya hai? What do you mean by only for chaining? Only for chaining means I cannot put chain through this obstacle, but I can see past the obstacle. Standing on one side of the obstacle, I can see the other side. That means I can do ranging, but I cannot put a chain through the obstacle. Give me an example for this. Give me an example for this. Yes, very good. There is a water body. Absolutely correct. Everybody got that correct, right? It is nothing but a water body. So standing on one side of a lake, can you see the other side of the lake? Yes. Standing on one side of the lake, you can see the other side of the lake. Yes or no? Yes. But can you put a chain through that particular lake? No. If you want, you can go and put the chain, but you will not get it back. Okay. Next obstacle is obstacle only for ranging. What do you mean by that? Only for ranging. Only for ranging means you cannot see past the obstacle. But you can put a chain through that particular obstacle. What is the example for that? It would be nothing but a fast. Okay, yes. Yeah. So, my question is this, right? Whenever you come across obstacles like this, say building, water bodies, dense forest, do you really think that we will stop our chain survey and go home? Do we stop our chain survey and go home? Please say yes or no. Very good, no. We don't stop our chain survey. What we will do is, we will set out right angles. And we will, find the solutions to this right angles. For example, you imagine there is a building here like this. This is a big building. And you need to run your chain through that big building. You need to run your chain through this big building. But you cannot measure this particular length A. So what you do is, at this point A, you can set out a right angle like this. Right? You can set a right angle like this. You can set a 45 degree if you want by using the French cross. Okay. So this length you can measure as L1. This length you measure as L2. So now you can find out AB is equal to what? Under root of L2 square minus L1 square. Okay. So please don't think that whenever we come across an obstacle, we stop our work. No, we don't stop any work. What we basically do is, we will set out right angles and we'll form solutions to this particular right angle. This is what we do. Okay. So these are the different obstacles in chain survey. Right. Now, one of the very important discussion that you need to remember is the degree of accuracy in chain survey. So there are a few conditions where we can get maximum degree of accuracy and a few conditions where our degree of accuracy is very bad. Let's look at that one by one. So you see the first one. Whenever I am taking measurements, for measurements with invar tape, right? Most accurate tape, spring balance to measure the field pull, thermometer to measure the field temperature. What is the accuracy I can achieve? It is 1 in 10,000. The accuracy I can achieve here is what? 1 in 10,000. Okay. What do you mean by that? Degree of accuracy is 1 in 10,000. What is the meaning of that? It means that after every 10,000 units only, I will get an error of 1 unit. After every 10,000 unit only, I will get an error of 1 unit. That is the understanding, which is very good. But you see, as the condition changes, what happens? If you are doing ordinary measurements with the steel tape, that means no invar tape. Plumb bob is used for verticality of ranging rods. Chain arrows, straight pins are also used. Then, drastically, there is a 10x reduction in accuracy. 10 times reduction is there in the accuracy. From 1 in 10,000, it reduces to 1 in 1,000. Okay, yes. Similarly, for measurements made with the tested chains and plumb bobs, the same 1 in 1,000 accuracy only you can receive. Right. If the condition is very average, then it is 1 in 500. But if the condition is rough or hilly, it is 1 in 250. So you see, there is a 40 times reduction in accuracy. Initially, if under the perfect conditions, with the best instruments, I can get 1 in 10,000. But when it is rough and hilly, right, what will happen? There's a 40 times reduction in accuracy. 40 times reduction in accuracy. Okay. So that condition is what we call it as rough or hilly ground. This is the reason why we say chain surveying is not suitable for rough and hilly terrains. Okay. This is why we say chain surveying is not suitable for rough or hilly terrains. Please remember that. Okay. That's it. So that's a discussion regarding the degree of accuracy in chains. That's it. Okay. So that is the end of our chapter here. Okay. That is the end of our chapter. Now let us try and remember what are the things that we studied here. Okay, let us quickly go through that. So what is the summary? First and foremost, we discussed about the four methods of linear measurements: direct distance measurement, optical distance measurement, as well as EDMI followed by approximate methods. We discussed about the principle of chain surveying, chain triangulation, everything we discussed. Well conditioned triangle also we saw. We saw the five terminologies. What is main survey station, main survey lines, check lines, right, baseline, after that offsets and tie lines. Right. After that, we saw the instruments used: chain tape, arrows, wooden peg, ranging rod, cross staff, everything we discussed. After that, we talked about ranging. What are the methods of ranging? Remember the field condition. Similarly, chaining we discussed and different methods. The first method is very important. Okay, that is method of stepping. It is always conducted downhill. Next, we discussed about the error due to incorrect chain, which is the most important concept here for problem solving. Okay. Next, errors in chain surveying we discussed cumulative and compensating errors. For the compensating errors, we discussed, for the cumulative errors, we discussed the chain correction. After that, we discussed today regarding the instruments used to set out right angles, the obstacles in chain surveying. Finally, we saw the degree of accuracy in chain surveying. One more topic that is there is the limiting length of the offset, but that is only there for engineering services. That discussion is only there for our engineering services, not really for our gauge students. So we will keep that discussion for a later stage. When I take only for ESE, I'll try and have that particular discussion. Okay? Yes. So that's it, right? Let us now try and start. Problem chain. Okay. Okay. So let us look at the problems here one by one. Please try this problem. I'll give you 2 minutes. Please try this problem. So let us try to solve that. Just give me a second. Just one second, give me. Let us try and solve this, okay? So they are saying that 30 kilometer tape is subject to a pull of 10 kg in 3 equal spans of 10 meters. Cross-sectional area, density of the tape are given below. The correction for sag is dash. Okay. So what is the formula for correction for sag? Total weight the whole square into total length divided by 24 t square n square sin is negative. Now total length is 30 meters. Full applied is 10 kg. Number of bays 3 equal spans. Number of bays 3. Now weight is not given, but density is given. 7.86 gram per centimeter cube. Cross-sectional area is given as 0.08 centimeter square. Right. Now from this, we need to find out our weight. Now what do you mean by density here? Density is nothing but mass by volume. How can I write volume as? Volume is nothing but cross-sectional area into length. So then what is mass? Mass will be nothing but density into area into length. Let us find out this mass. Density is 7.86 gram per centimeter cube multiplied by cross-sectional area is 0.08 centimeter square multiplied with the what is the unit of length? If I provided it in meter unit, nothing will cancel off. So what will I do? I will multiply that with 100 and I'll substitute the length in centimeter cube. So numerator will be centimeter cube. Numerator will be centimeter cube. Denominator will be centimeter cube. This will cancel and you'll get the mass unit in gram. Can anybody please tell me what is the gram unit is? What is the gram? What is the weight of that particular chain in grams? Lalita, please tell me what is the value you got? 628.8. Really? 628 you got? Yes. I think Saiteja and Bhargav Teja is correct. We'll get it as 1,886.4 grams. Okay. Which is nothing but 1.8864 kgs. This is the mass of the chain, which means the chain is roughly 2 kilograms. Now please understand, the unit of pull is kilogram. So we can also put the weight unit in kilogram. Because please understand, the pull and weight are supposed to be Newton. They are supposed to be force units. But they did not give us the force unit. They are giving us the mass unit. That is in kg. So if both the W and P are the same unit, we can substitute that. We need not convert them into newtons. No need. Because numerator and denominator, if they are the same units, they will cancel off. So I will not convert it into any units. Now we can go for direct substitution. What is the correction for sag? It will be equal to total weight 1.8864 in the whole square into total length divided by 24 into p square into n square. The sign is negative. Right. Now what is the answer you get? 0.0049 meters. Yes or no? I think Lalita got the answer. Lalita got the mass wrong, but the answer correct. Are you getting this answer? Please yes or no? Are you getting this answer? Please yes or no? Yes. Okay. Try the next problem. Please try this. Okay, let us try and solve this. So a 50-meter tape is suspended between two ends under a pull of 150 Newton. The weight of the tape is 25 Newton. The current distance is dash. So here you see weight is given in Newton units and the pull is also given in Newton units. Both are force unit. In the previous example, both were in mass units, so no problem. Here both are in Newton units, so again no problem. Right, so length of the tape is given as 50 meter. Pull applied is given as 150 Newton. Weight of the tape is given as 25 Newton. Now, right, they are asking you for the correct distance. Which correction will apply here? Sag correction. The total weight, the whole square into total length, divided by 24 t square x square. Okay, the sign is always negative. So what is weight? 25 square, length of 50, 24 kilo, 150 square, and 2 ends. 2 ends means n is equal to 1. 2 end only means n is equal to 1. What is the value for this sag correction? Tell me. How much you got sag correction as? Minus 0.05, sir. So no? Yes. Now what are they asking you finally? They are asking you for the correct length. Right, so it is measured length 50 plus minus 0.057. 49.49. 49.94 should be okay. Answers option B. 49.94. I hope you got the answers, everybody. Very good. Tell me, how will you apply pull correction, Bhargav Teja? To apply pull correction, you need a cross-sectional area, we need a Young's models, all these things. Now, they did not provide that. If it is provided, yes, you can apply also. If it is provided, then you can apply. If that is not necessary, they will not provide you with that. Okay, if it is not necessary, they will not really provide you with that. Okay, it's a good question. I hope you understood that. Okay, moving on to the next question. Please solve this. Okay, let us try and solve this problem here. So which correction we need to apply here? The length of a base line measured on the ground at an elevation of 200 meters above is 2500. The required correction to reduce to mean sea level. So reduction to mean sea level is calculated as L into H by R. Right, so H is above, so the sign should be what? Minus. Right, so remember, if it is above, we are trying to project it down, so the correction would be negative. So what is L here? L is 2500 meters. How much above? 200 meters above. What is the radius of the earth? 6370 into 1000 meters. Right. Direct substitution only. Remember, the sign is negative. What's the answer you get? Minus of. What's the answer you got? Minus 0.0785 meters. Right. So that is nothing but option A. Yes. Try the next problem. This is what we already solved now. Yes. Try the fourth problem. Try this. So please draw a figure for this. Okay. If you are able to draw a figure, you will get the answer. Okay. Please try it. So let us see. To continue survey line AB past an obstacle, a line BC 250 meter long was set out perpendicular to AB from C. Angles BCD and BCE were set out as 60 and 45 degree. So the point is to continue a survey line past an obstacle, right? So there is already a line AB. There is already a line AB. Okay. What we are trying to do is we are trying to continue it past an obstacle like this. So this is my obstacle. We are trying to continue it past the obstacle. For that, a line BC 250 meters long was set out perpendicular to AB, right? And now angles BCE and BCD were set out 60, 45. If ED is made on the same line of AB, so if E and D are on the same line of AB, what is the length of CE and CD? Okay, so this is BCE. This is BCD. Okay, so these angles are given to me as 60 degree, and these angles are given to me as 45 degree. Yes. So how do I find it? So if I take cos 45 degree, what is cos 45 degree? Or cos would be what? Adjacent side, that is BC by hypotenuse CE, right? So BC is given to me as 250 meter. CE I need to find out. So what is the value of CE? CE would be nothing but 250 by cos 45 degrees. What is the value of CE? Anybody? What is the value of CE? Yes, 353.55. 353.55 meters. Similarly, what would be CD? If I take cos 60 degrees, I'll get it as BC by CD. What is CD is equal to BC 250 meter by cos 60. That will come out to be what? 500 meters. So CD, they are asking you for CD and C in the same order. CD and C. CD is what? 500. C is what? 354. That's it. That's it. Right, that is our length. Okay, yes. So this is it. Okay, you need to read the question carefully and draw the figures. By the 11th question now. Please try this. (20°C) and 10 kg pull is used to measure a baseline. The true length of the tape at the time of measurement, if the temperature was 50°C, coefficient of linear expansion is 10 power minus 6. Let us write down the data. Length of the tape is 50 meters. Okay. Temperature at standardization is 20 degrees Celsius. Pull at standardization is what? 10 kg. What is the temperature at measurement? 50 degrees Celsius, right? And alpha is equal to 10 power minus 6 per degree Celsius. Now, is there pull at measurement given? Yes or no? In this question, is pull at measurement given? Not given. So if it is not given, forget about the pull correction. You just need to apply here temperature correction. So what is correction for temperature? Alpha into Tm minus T naught into A. Had they mentioned the pull also, you will have to apply the pull correction. Okay. So 10 power minus 6. 10 power minus 6 into what is temperature during measurement? 50. Temperature during standardization 20. Length of the chain is 50. So 30 into 50, 1500. 4. So minus, so it will be plus 0.0015 meters. That is a correction for temperature. So finally they are asking for correct length. Correct length is equal to measured length plus correction. So 50 plus 0.001%. 2.001. That's it. That is our correction. Okay, that's it. Okay, I hope you got the answer here. Yes, very good. Srikanta Bhargav, I don't know why you got 0.02. Yes. Right, now let us do this problem here. This was a previous year ESC prelims question. Please try and solve this. Please try and solve this. In passing an obstacle in the form of a pond, stations A and D on a survey line were taken on the opposite sides of the pond. On the left of AD, a line AB 240 meters long was laid, and the second line AC 300 meters long was arranged on the right of it. Points B, D, and C being on the same straight line. BD and DC were changed and found to be 150 and 180 respectively. The width of the pond AD is dash. The width of the pond AD is dash. So this was a ESC prelims question. Okay. Please try it again. You have to draw a figure, obviously. If you draw a figure, you'll get the answer. Okay. Please proceed. How the surveyor is going? The surveyor stations A and so let us see how you have done this. See whether you have drawn similarly or not. There is an obstacle like this, okay, in the form of a pond, and stations A and D are taken on the opposite sides of the pond. A and D are taken on the opposite side of the pond. To the left and right of AD, we have taken the line. So what is the left and right? Please understand, this is the left and the right of the line. Because we need to talk about how the surveyor is going. The surveyor is going in this direction. So this is the left and right of the surveyor. This is the front and back of the surveyor. That is not left and right of the AD. So you need to think about with the perspective of the surveyor. Okay, left and right of the surveyor will be like that. Right. So whatever this is behind the surveyor, this is in front of the surveyor. Please understand. So that is the first basic point. You have taken a line AD, right, on the left of AB. So this is say AB, and this is say AC. This is AC. Now they are saying that B, D, and C are in the same straight line. B, D, and C are in the same straight line. So can I take B, D, and C like this? Yes or no? If I am taking B, D, and C like this, what is the angle between the line BC and AD? If you take like this, now you are going to get the relation as the angle between BD and DC and AD as 90 degree. You get like this. Now BD is given as 150 meter and DC is given as 180 meter. AB, DC, everything is given. So since there is a 90 degree angle, our calculation becomes very, very easy, but the answer becomes absolutely wrong. Because they did not say that, the line BC is perpendicular to AD. They just told that B, D, and C are the same straight line, which means this is also a possibility. Right now, B, D, and C can be like this also. This is also a possibility. So until and until they have mentioned that two lines are perpendicular, please don't make them perpendicular. Similarly, B, D, and C can be like this also. Like no issues. They just told that B, D, and C are in the same straight line. That is the only information they are giving you, which means I can take B, D, and C like this. So this is my point of view. Okay. So do not try and make any 90 degrees unless they have mentioned there is 90 degree. That is one point that you need to remember. Yes. So let us write down the data they have provided. AB is 240 meters long. AC is what? 300 meters long. BD is 150 meters long, and DC is 180 meters long. Okay. What is this angle? What is this angle? This angle I will take it as theta. Okay. Let me just try and take it as theta. Because you see, if you are having a triangle, because basically this figure looks like a triangle, in which you know all the sides. If there is a triangle in which all the sides are known, then the answer will be calculated by, cosine rule. If there is a triangle in which all the angles will be known, your answer will be always by sine rule. So since there is a triangle, you know all the sides of the triangle, the solution will be by the cosine rule. So I'll take theta angle there, right? And the theta is common in the triangle ABC and also in the triangle ADC. Now the unknown here is AD. So in the big triangle ABC, what is the value of cos theta? What is the value of cos theta? Cos theta is nothing but AC square plus BC square minus AB square divided by 2 times AC into BC. Now similarly in the triangle ADC, what is the value of cos theta? Cos theta is equal to AC square plus DC square minus AD square divided by 2 times AC into DC. Divided by 2 times AC into DC. Okay. Right. Now what is AC? AC is 300 square, right? Plus DC is, what is DC? 150 plus 180, 330 the whole square. Minus AB is what? 240 the whole square. Divided by 2 into 300 into 330 should be equal to AC, that is 300 square, plus DC. What is DC? 180 square minus AD, I need to find out, divided by 2 into 300 into, right, what is DC? 180. So from this 2 times the numerator, 2 times 300, 2 times 300 will cancel, and you will get the value of AD. Okay. Now you can solve the value of AD yourself, right? It's going to be a lengthy calculation. Now, as I told you, this was an ESC prelims question. Can you solve this without calci? No. Right. You have reached a point that beyond this, you cannot solve it without calci. Beyond this point, without calci, you cannot solve it. So such problems should be left alone. Okay. You need to try it. You need to see whether calci is required or not. And you reach a point where without calci, it is not at all possible to go forward. Then don't try to solve based too much time. Okay, because if you cannot solve it, obviously nobody else can solve it. But you see, so what if some approximations can be done and it can be solved or not? You have to obviously see that. Okay. Yes. So anyway, you please leave that solution here. You can try it after the class. Okay. Yes. Let us try the last problem here. Let us try this problem here. If a chain is found to be too long, it may be adjusted by, right? What is the first option saying? First option that they say is A. If a chain is found to be too long, it may be adjusted by closing the opened joints of the rings. Yes or no? Yes. See, the rings are supposed to be closed. The rings are supposed to be closed. But if the rings are opening up like this, what will happen to the effective length? The effective length will increase. Yes or no? And if the same rings are closed, the effective length will decrease. The effective length will decrease. Okay. So if the chain is found to be too long, right, this makes my chain too long, and this is making my chain correct. Is it correct or not? Yes. So that first statement is correct. Right. Next step. Removing one or more circular rings. Is that true or false? Yes. Right. That is also true. Because if sometimes the chain will be too long and almost all the rings will be close to position only. This increasing length may be because of the extension of the link, that 4 mm diameter wires are another link. That particular link may have extended little by little for almost all the links. That is the reason why the chain is coming as too long. Then rather than removing a link, maybe if you remove one ring, you may be able to make it shorter. Yes. Now some of you might feel that, sir, is that standard procedure or not? The answer is yes, it is a standard procedure. Yes. So one, you can take some textbook material and refer. Yes, that is a standard procedure. Right. Now what is statement C? Statement C says that replacing worn out rings. See, if this is a ring here, if this is a circular ring here, okay, once again, so I'll draw like this and like this. So if you imagine this is the circular ring here, right, as the keep on pulling happens, as you keep on applying pull from this direction, what happens is this particular portion of the ring will be eroded away, right? This particular portion of the ring will be eroded away, and what will happen? The effective length of the chain will increase. Like as erosion, as you keep on pulling it now, like slowly, this portion is worn out, right? So as this particular portion is worn out, what will happen? As that portion is worn out, what will happen? What will happen is that the effective length will increase. As that is happening, the effective length of the chain will increase. So if you replace that, what will happen? Will the length become shorter? Yes or no? Yes. So is that statement true? Yes. What about statement number D? Straightening the bend links. The answer is no. Right? Because if you're having a link that is bent like this, so you imagine you're having a link that is bent like this, and if you are going to straighten it up, what will happen is it will increase the length. It increases the length. So this is not really what we want. Okay. So that particular statement, that D, is false. So which are the proper ways of adjusting A, B, and C? That's it. Okay. Yes. So these are the proper way in which you can adjust your chain. Okay. Yes. 120 meter for the previous question is not correct. Nothing. 120 is the answer here. Okay. So yes. So that's it. That is the different problems in this chapter. Okay. And we'll stop here. Okay. Now I will give you this as a homework.